Hello, and welcome to the stream. We're gonna wait a few minutes. Oh, hi, Jack. I'm not a professor, but anyway, yeah, um, yeah, just call me Ming. That's okay. Um, oh, hi, Vernon. Hi, PVM. Wow, already 12 people. I saw this is early, huh? Because in North America, I mean, in Eastern Standard Time is 8 a.m. As you can see in the right corner of my screen. It's still early. Where are you guys from? Subtitles? Unfortunately, I don't have live subtitle. Is that even a feature? Like when you stream, there's just gonna be like AI generated automatic subtitle. Is there such a thing? In Italy, great. Wait, Edor, did was it you who requested the stream? Julius, France. Because this stream was scheduled upon request by a viewer in my Discord server. So, Edor, are you that person? I know YouTube can generate it after the stream. Yeah, you can generate after the stream. I know that, right? That's how I add subtitles in my videos. Yeah, not live, unfortunately. Yeah, so this is something I cannot provide at the moment. Unfortunate, but still. Anyway, so that's the if you guys can see the screen, the link to the file is in the description. And hello from France. Ah, a lot of people from Europe, huh? Because it's perhaps more convenient um, for Europe, for European viewers at this moment. No, I didn't request it. Okay, that's okay. Because I remember a guy in my, presumably a guy in my Discord wanted a stream on mass finance. You have a series on of stream a specific subject to be like a course. Thank you for your amazing work. Well, Bishop. Well, the thing is, um, I have to be highly selective. Even though there's tons of amazing subjects out there, I cannot afford to make um, course for every subject. That's just unfeasible. This is a one-man operation. Right now, they're already sort of, at least that's the plan anyway. There's three courses, more or less official courses going on the channel, right? And to our video uploads, stochastic calculus and complex variables. I know I should really upload videos on those two series. And also I have weekly measure theory the seminars. You can call it a seminar, but basically that's like a course as well. So if I put another course simultaneously while I'm doing all of that, I'm just gonna burn out. I know my limit. Okay, so um, the streaming schedule, as I mentioned a few streams back, is currently three streams per week. Okay, three streams, and each has a length of approximately 4 to 5 hours, which is a lot. Let's be honest. So two of them have fixed topics. Okay, two of them has fixed topic. One's measure theory, as mentioned, which is on Tuesday regularly. Another one is on mathematical statistics and exterior ballistics, which is on Sunday. So these are all like basically courses. And on Saturday, which is well today, the topic is more flexible. So it really depends. If somebody requested a topic in my Discord and I can find something appropriate, I'll stream it. If not, I'll just do something else. Okay, I used to do like my first attempt on abstract algebra on my 2.0 channel, but because of the topic request, right now that has gone dormant. Okay, unfortunate, but this is like I figured if people request a topic and I don't do it, then what's the point of the topic request feature in my Discord, right? So yeah, yes. So Bishop, so if I mean as I mentioned, like right now I already have 3 courses. If something that you wanted is not among them, I'm sorry, but we'll just have to keep things that way. The next Saturday is on information theory. It's very consistent with the type of subject in the channel. Next Saturday actually is already I haven't officially posted yet, but next Saturday is on optimal control. Okay, but I'll keep information theory in the for the next one. Okay, so the one after next Saturday. Okay, so how about that? Yeah. Yeah, thank you very much for your interest. Okay. So, okay. Let's start with the main subject today, which is mathematical finance. So, so for Saturday stream, I'm more or less okay. We will do actual math, of course, but at the same time, we cannot afford to be completely thorough because these aren't courses. So you can think of Saturday streams as me pointing out resources. Do you have PhD? No, I don't. I have a master's degree in applied mathematics. So here, this is mathematical finance, and I'll be completely honest. I'm not a quant. Okay, I'm not a quant. So even though I'm familiar with part of it, part of the mathematical finance, I'm not a professional. Okay, so the format or the style of the stream is very much going to be like a seminar. We're already doing that sort of seminar thing in the measure theory live stream. Okay, in that theory, I pretend to be a beginner. I pretend to be a beginner because, as I understand, the measure theory can be highly non-intuitive for a beginner. So if I assume the role of a lecturer, so to say, and I just do everything as if they are natural, then probably it's going to be difficult for beginners to follow. So in that case, in the measure theory stream, I pretend to be a beginner. Okay, but for mathematical finance, I'm an actual beginner. Okay, I'm an actual beginner. So hopefully, it's so be very. So I would just say, put. I mean, how do you put that in English? A grain of salt. Yeah, take what I say with a grain of salt. Take a grain of. If something I say don't make sense, it probably doesn't. Okay, and be sure to call it out in chat. Okay, and on mathematical finance, I'm in no position to give lectures. Okay, but because I find the topic interesting, and a lot of people find the topic interesting, so why don't we just figure things out together? Okay, so here, without further ado, let's get into the main material. Here we have a set of notes called Introduction to Mathematics of Finance, from risk management to option pricing, for options pricing, by Dr. Stephen Roman, professors of mathematics in California State University, Fullerton. Okay, so this is a very approachable set of notes. Okay, this is pretty much a book. Okay? This is pretty much a book, and God bless Professor Steve Roman for putting it out for free. Okay, and the contents are absolutely standard. Okay, so these are the fundamental topics you should know before getting into more advanced models. For more advanced models, of course, these are models that are perhaps a little bit too simplistic for real applications, but more complicated models are always built upon modifications of simpler models. So these are still of tremendous values. And also at the same time, in reality, there's this tendency and temptation for practitioners to employ ever more complex model in the hope of capturing intricacies, which is totally natural, an innocent choice. But sometimes the more complicated model doesn't always necessarily lead to better results, which is also a fact of life. So you can't just do math out of your way to bypass reality. So it's a good opportunity for us to discuss modeling assumptions and whatnot. Okay. So let's look at the preface, and we'll briefly look at, let's take a look at the content, a list of content, and we'll briefly look at the preface, so we can get an idea of what to expect. As I mentioned, the set of notes is highly approachable. It only assumes basic calculus and linear algebra. It does not even assume probability theory. Although, for the sake of our stream, I will probably assume a little bit of a probability theory. If something isn't clear, okay, if something isn't super well known when it comes to probability stuff, we'll do a review on a need-to-know basis. But as far as the book is concerned, it starts from ground up. It does not even assume basic probability, so it's highly approachable. Chapter 1, Probability 1, Introduction to Discrete Probability. Okay, the binomial distribution, all that stuff. Chapter 2, Portfolio Management and Capital Asset Pricing Model, CAPM. So in Chapter 2 already, you have you're diving into the core of the subject. Okay, so you're not. I like how it is arranged, because as you can see, the probability chapters are scattered across. Can you recap of what we're working on today? Today we're doing mathematical finance. Actually, I haven't laid out the plan for today. Okay, so I'm planning to have a 4-hour, perhaps a little bit longer, 5. I mean, specific topic in math finance. So good question. So we're going to look at chapter 2 for sure, and perhaps chapter 3. Okay, and because this is a one-off stream, I haven't decided. I mean, I probably can't make it a series at this moment, which is unfortunate, because my hands are pretty, my plates are pretty full. So because this is a one-off stream, so we're going to do like an overview for risk management and option pricing, so to see what them are about. Okay, and some level of detail. Okay, but not completely thorough. Okay, if that's okay. I'm just, for Saturday streams, I'm more or less like kind of pointing out resources. You can even think of them as extended book reviews. Book review videos are popular on YouTube, right? But typically there aren't super in depth, let's be honest. But here you can think of it as me reviewing certain chapters. Hi Wendell, don't be sorry. So yeah, power trading. That's what we're going to do. Probably we're not going to get to Black-Scholes, but don't worry, Black-Scholes will be covered in the stochastic main series, which is coming very soon. Okay, so I was talking about Chapter 2, Portfolio Management, and Capital Asset Pricing Model, also known as CAPM, CAPM, pronounced as CAPM model, very classic model, won the Nobel Prize in Economics. Sounds good. I took Intro to Math Finance course in Iowa State and looking for this as a nice refresher. Thank you very much. You're actually probably more knowledgeable than me. Okay, so don't hesitate if I say something nonsensical. Okay, if don't be afraid to call me out in chat if I say something nonsensical. Okay, so on this channel, I don't care about quote unquote saving face. Okay, there's no persona to keep up. We're here for the truth and nothing but the truth. Okay, if I make a mistake, I'll be very happy if someone can point that out for me. Okay, chapter 3, background and options. Background and options. So this is something we also need to cover in the stochastic series. I did not like this subject back in the uni. I was interested in probability perspective, but dislike the overall subject. Okay. If you can, but if you can share your thoughts on why you dislike it, then go ahead and in chat. I figured this is mathematical finance. I mean, I'm not an expert, right? So it's hard for me to form an opinion on it. But I think this is something that holds tremendous power in modern society. Mathematical finance, the modeling, it informs so many decisions that are that shapes the fate of millions of families. Right? Think about the 2008 financial crisis. Right? Mathematics also played a part in the erroneous, so to say, decision making. So Hai Ming just asking how was the preface to this learning. What is the preface? Yeah, we'll get to the preface soon. Okay, this is just a list of content. We'll take a look at that very soon. And by the way, if you can just go to the stream link. Okay, go to the stream description, and you can download the PDF yourself. Yeah, it's the backbone of our society by now. You cannot afford to be completely ignorant of it, right? Would you be more mathematical? Yes. So in this is math finance after all. It's going to be mathematical, and it's going to be also some domain knowledge, obviously. So let's tolerate each other's ignorance. So some might have more background in finance than in math, and some might have more background in math and finance. We'll try to balance the two. Mathematics or bad model assumption. Well, applied mathematics, right? So applied mathematics constitute model assumptions. Yeah, I'm talking about the so-called Gaussian copula. If you guys heard of it. So this is something that is quite widely discussed in the math finance community, Gaussian copula. So basically, Gaussian copula is a model on a very simplistic level. So a Gaussian copula is a model that fits a joint distribution from marginal distribution, because high dimensional joint distributions are very difficult to directly model. Okay, so the copula, and in particular Gaussian copula, is a class of model that allows us to model joint distribution. So you want to, why do we care? So you want to model the risk of simultaneous simultaneous speed default. A lot of people can't pay their bills, okay, can't pay their debt. You want to model that sort of event. And the models, the Gaussian copula model, wasn't quite enough to capture the whole risk, and many instruments were priced according to that wrong information. Okay, but anyway, I'm not an expert. But anyway, so here chapter 3 is on background on options. So this is very much finance, more finance than math. I would say arbitrage, arbitrage. So option pricing. Option pricing is based on the assumption of no arbitrage, basically no free lunch. Chapter 5, probability 2, more discrete probability. Perhaps some stochastic processes. Chapter 6, discrete time pricing models. Chapter 7, the Cox-Ross-Rubinson model. This one I never even heard of. Chapter 8, continuous probability. Chapter 10, the famous Black-Scholes option pricing formula. Once again, this is just like in chapter 2, the CAP-M model. Black-Scholes is also a Nobel Prize winning discovery. All right, I can say this as a fact that these derivatives of nonlinear equations are very important. Exactly, right? They hold tremendous power over modern society. So whether we like it or not, we cannot afford to be ignorant of it. Okay, this is not just a fun intellectual puzzle. This holds tremendous stake. Okay, so we're doing something that is very profound here. Okay, what a self-important comment. Okay, sorry guys. Chapter 10, option pricing and American option. So this is once again a huge topic. Actually, option pricing. Optimal stopping, not option price. Optimal stopping and American option. Optimal stopping is a huge topic in applied mathematics. It has to do with the subject called dynamic programming. Dynamic programming. So it's making optimal decision sequentially, basically. And we have an appendix on convexity and separation. Okay. Anyway, so that's the preface. So let's take a look at the that's the content. That's the content. So let's take a look at the preface. We're not gonna read the whole thing, but just we're keeping our eye on the main background. Okay, what's the prerequisite for the subject? Because that's what everyone is worried about when approaching a new subject. Fortunately, the prerequisite for this book is very modest. This book covers two main areas of mathematical finance, areas that culminated in work worthy of Nobel Prize in economics. One is portfolio risk management, culminating in the CAP-M model, and the other is the asset pricing theory. So, culminating in the Black-Scholes option pricing formula. Our discussion of portfolio risk management takes a single chapter. The rest of the book is devoted to the study of asset pricing model. I see. Okay, so very much the rest of the chapter 3 all the way to 10 are for option pricing. Once again, this is a huge topic. So let's take a look at the intended audience. The intended audience is upper division undergraduate or beginning graduate student in applied math, in mathematics, finance, or economics. Accordingly, no measure theory is used in the book. Do you guys like that? No measure theory is used in the book. Hey, Adrian. So, yeah, it's quite approachable, and not even probability is assumed. Okay, I realize the book may be read by people with rather diverse backgrounds. On one hand, students of mathematics may be well prepared in the ways of mathematical thinking, but not so well prepared when it comes to matters related to finance, portfolio, stock options, forward contracts, and so on. So these are financial instruments. Options and forward contracts, these are financial instruments. So a portfolio is like a bunch of assets. Okay. On the other hand, students of finance and economics may be well versed in financial topics, but not as mathematically minded as students of mathematics. Right? So it's kind of like on Sunday when we how we did the ballistic stream, ballistics and and mathematical statistics. Right? In the preface, the author said, physicists might find the math, physicists might find the physics trivial, and mathematicians might find the math trivial, but let's tolerate each other's ignorance. So here we're asking everyone to do the same. So some people might be more well prepared in mathematics, some people might be more prepared in finance. So let's tolerate each other's ignorance. Okay. So yeah, since the subject of this book is the mathematics of finance, this is italicized, so this book is pretty mathematical. I have not watered down the mathematics in any way, appropriate to the level, of course. Unfortunately, no. Garch and arts, that's you will find those topic in time series analysis. Okay, so this book is very much theoretical. This book is very much theoretical. It does not cover like empirical methods, data analytic methods such as Garch. Garch is a time series model. You'll find that in like time series books. Okay, but I'm not sure if I can do a time series stream because my favorite time series book apparently it's still copyrighted. I cannot stream it, but perhaps we'll make videos down the road. Okay, so anyway, here, but I mean, if you guys have good time series like notes and whatever, feel free to send it to me or recommend it in chat. You can send me to my Discord or whatever, and I'll take a look. Because time series is perhaps also a huge interest among my viewers. All right, so this book, as I said, is very much a theoretical book. Garch and arts, these are specific modeling tools. Right? More of an econometric, yeah, exactly. Yeah, econometric. You can certainly call it that way. Time series analysis is a huge common area between statistics and econometric, and also signal processing. Okay, I also made an effort to make the book mathematically self-contained as possible. Thank you very much. Aside from a certain comfort level with mathematical thinking, a freshman sophomore course on linear algebra is more than enough. Wow. Well, I think you do need some calculus. You do need some calculus, but nothing insane as real analysis. Okay, as far as real analysis is concerned. In particular, the reader should be comfortable with matrix algebra, the notion of vector space, and the kernel range of linear transformation. Because these are what the quizzes in the community tab is for. Okay. The method of Lagrange multiplier is used as a couple of proofs related to risk management, but these proofs can be skimmed or omitted if desired. Okay, Lagrange multiplier. This is a topic in multivariable calculus. Optimization under constraint. And as we'll see in CAPM, right, the capital asset pricing model, CAPM model, it uses Lagrange multipliers. Of course, probability theory is ever present in the area of mathematical finance. In this respect, the book is self-contained. Okay? It does not assume probability. Okay? Several chapters on probability theory are placed at appropriate places throughout the book. Actually, I like this approach very much because sometimes in applied mathematics, you do so much like machinery until you're exhausted and the applications feel like an afterthought. And here, this is not the case. Right? In chapter 2, you already have the meat and potato of the main subject, which is very cool. The idea is to provide necessary theory on a need-to-know basis, exactly. In this way, readers who choose not to cover the continuous pricing theory, for example, need not deal with matters related to continuous probability. Okay, so the first chapter is mostly a review. Okay, so we'll just take a brief look at the first chapter and we'll dive straight into chapter 2. Okay, so we will ignore the rest of the preface and continue. And of course, as we always should do, when it comes to things like, I have a request, can you do a video on solving complex nonlinear equations with method dimension like like random matrix theory? Try to master. Sure, you can put it. Yeah, okay. Since you already put it here, I'll write it down. we're talking about nonlinear equations, solving nonlinear equations. This is, of course, entire discipline. If you have something more specific, like, please let me know. Okay, so yeah, there's a topic request channel on Discord. That's true. That's certainly true. You can be more thorough and go into whatever that you prefer over there. But yeah, I'll put that down. Thank you very much for the request. Okay, power trading. Okay. Said nonlinear equation solving. This is, I think, research level stuff. Huh? Nonlinear equations with methods of dimension reduction, like random matrix theory. I'll see what I can do. Okay, I put it down in my notes. All right, so let's continue. So here we have a brief introduction, okay, just at the high level stuff. Okay, so in the introduction section, let me just zoom in a little bit. Okay. Introduction section, we have a section on portfolio risk management. And here and next we have option pricing model. So let's first take a look at the portfolio risk management section and dive straight into the main part. Risk is an inevitable side effect of the effort to make more money than the next guy. Yeah, very true. To be sure, money makes money, and this process can be carried out without any significant measure of risk. All an investor needs to do is buy United States Treasury bonds, generally considered to be risk-free investment. The price paid for such investment is generally a boring rate of return. Okay, so these are riskless. These are riskless assets. Of course, that's an approximation. The real problem is that if everyone makes the same rate of return, then this return serves only to maintain the status quo. And put another way, if you want to buy a Rolls Royce or a yacht or even a Rolex watch, then you need to make more money than the next guy, and this requires taking risk. Okay, you see, okay, this is greed, basically. Okay, the first problem is to decide how to quantify the level of risk of an asset. Quantifying risk. This is what we're going about. Okay. How to quantify the level of risk of an asset. It turns out to be simple. However, like the rest of life, simple answers often turn out to be incomplete. In particular, not only is it important to measure an asset's risk, but it is essential to measure the risk that results from the asset's interaction with other assets in a portfolio. Interaction with other assets in the portfolio, that's an important aspect we need to think about. Interaction. So probabilistically, this probably means things like correlation, covariance. Right? So yeah, somebody was just talking about the covariance matrices in chat. Power trading again. After all, in the end, it is the performance of an investor's entire portfolio that separates one investor from another. Now, people don't want to be rich, they just want to be richer than their peers. Okay, of course, the future return of an asset is generally unknown in the present. In probabilistic terms, an asset return is a random variable. Okay, so to the return of an entire portfolio of assets. Okay, so we're going to use things like random variables and distributions to model return. However, it is not hard to see that by combining assets in a careful manner, it is possible to engineer the overall risk of a portfolio. Okay, so this is what we're going about. Like, how do you engineer the overall risk of portfolio? Possibly even to a point that is below the level of risk of each individual asset. This risk-lowering process of an asset is called diversification. Don't put all your eggs in one basket, as they say, right? So the intuition is pretty, well, intuitive, but how exactly do you overall minimize the risk, right? So that's the key here. Speaking more mathematically, it is generally accepted that a good measure of an asset risk is variance, or standard deviation, or return. So assuming the random variable is L2, then consider minimizing the variance. Of course, L2 theory has its own limitation. It does not cover things like extreme events like financial collapse, but that's a separate topic, right? There's separate disciplines such as extreme value theory in probability, okay, that does this sort of thing. But anyway, let's just first start with minimizing the variance, right? So that's minimizing risk. Let's first try minimizing variance, which amounts to basically a least square problem, right? Which is mathematically well understood. As the reader probably knows, the variance or standard deviation is a measure of the spread over possible values of a random variable. Okay, that's a good way to put it. So, the greater the variance, the greater is the probability that the risk will deviate significantly from the average. Right. So here, that's a colloquial statement for the Chebyshev inequality. Right. The Chebyshev inequality says the probability that the random variable deviates from the average can be bounded by the variance, divided by a scaling constant, basically. This is a Chebyshev inequality. By the same token, the covariance that's models the interaction within components of a portfolio. Right? The covariance of an asset return with respect to return of another asset portfolio provides a good measure of risk interaction. Right? That's the interaction. Okay, so already we have quite a high level understanding of what portfolio risk management is about. Right? So portfolio is a collection of assets. We wish to minimize risk. The risk, and in the same time, we want higher average return, right? Because we're greedy. Right? So what we do is, as a first step, is to minimize the variance. Okay. Thus, in portfolio management theory, one examines the expected value of an asset's return as well as variance and covariance with other assets. Only through these statistics can one determine whether adding a particular asset to a portfolio is justified based on a risk-return analysis. Okay, as we see, a remarkably simple procedure is provided by the capital asset pricing model, or CAPM. The CAPM leads to the notion of market portfolio, which is a portfolio of risky assets that has perfect diversification. Okay, so we'll see what this means. What does it mean by perfect diversification? Does it mean minimize variance or something else? We'll check it out. In theory, such a portfolio must contain a positive amount of every available asset in the universe. It must contain a positive amount of every available asset in the universe. So that's a feature. It cannot be zero. So imagine if you have a vector, which we will do, that represents a vector of real numbers to represent a portfolio. And here it says every entry should be positive in order to achieve perfect diversification. Okay, that's an interesting result. We'll see if we can find a mathematical statement in chapter 2. Okay, this is because all investors will want to invest exclusively in this portfolio, along with risk-free. Okay, this is because all investors will want to invest exclusively in this portfolio, along with risk-free assets, And so any asset that is not in the market portfolio will wither from neglect and die. What does this say? It says CAPM leads to a notion of market portfolio, which is a portfolio of risky asset leads to perfect diversification. And market portfolio must contain positive amount of every available asset in the universe. And here's why. Because all investors will want to invest exclusively in this portfolio. And so any asset that is not in the market portfolio will wither. Oh, okay. So it's kind of a natural selection, I guess. The idea is it's kind of a natural selection. What is not in the market portfolio eventually just, exit the market, basically. Not declared as a paragraph. I mean, this is a high-level description, after all, right? And the thing is, reality is always messier. Right? Reality is always, this is only a probably oversimplification, but that's okay. From a practical standpoint, the market portfolio is nothing but hot air. On the other hand, studies indicate that it is possible to approximate market portfolio by investing in a few dozen or so well-chosen assets. Fortunately, this also partially mitigates the problem of withering assets. Because an asset that doesn't make it into the investor's market portfolio may very well make it into another's portfolio. One investor's market portfolio may very well make it into another portfolio. Once the market portfolio or approximation thereof has been identified, there remains only one consideration for the rational investor, or at least in theory, and that is how much to invest in the risky portfolio and how much to invest in a risk-free asset. Okay, so in the market portfolio, everything is risky. Right? So have a positive variance, basically. Can I highlight things in this edit? Hang on. Why can I not highlight things? Okay, so in a market portfolio, as mentioned, everything is risky. But of course, you can also invest in risk-free portfolio. In a risk-free assets as well. And you need to balance the two, right? This is the main idea of no free lunch. The whole finance takes the assumption that there's no arbitrage, right? Arbitrage as you would mean you can make free money. Yeah, that's what I heard. That's what I heard. Is this called the efficient market hypothesis? Power trading. Correct me if I'm wrong. Is that called the efficient market hypothesis? So basically, the idea is if there's an opportunity to make free money, someone will immediately spot it, and this way, and that guy started to make a lot of money, and other people figure that out, and that opportunity just dies. So it's like a unstable situation. That's a hypothesis anyway. Okay, so why don't we just get into the main math? No, that's different. Sorry. Okay, that's different. Okay, totally. I totally made a fool of myself. That's totally okay. Let me just briefly search what is a efficient market hypothesis. What does that mean? I'm just dropping names without actually knowing them. Sorry about that. Let's try to educate myself. Efficient market hypothesis is a hypothesis of financial economics that states that asset prices reflect all information. That's different. Reflect all available information. A direct implication that it's impossible to beat the market consistently on a risk-adjusted basis, since market prices should only react to new information. Okay, so how is this a corollary? Is this a corollary of the no arbitrage hypothesis, or what's the relation between them? Perhaps that's too advanced for my level right now. Okay, but anyway, I'll take that as I'll just put it in my notes that EMH and no arbitrage may not mean exactly the same thing. Okay, efficient market hypothesis says that the price of the asset reflects already info. There's no there's no edge. There's no, I guess there's no opportunity to make free money. That's the idea? Okay. It's great that somebody pointed out the exact meaning of efficient market hypothesis. Awesome. So why don't we get to yeah, so actually it's here, right? It's here. As we'll see, the key principle behind asset pricing is the notion that the market tries to avoid arbitrage. More specifically, if an arbitrage opportunity exists, then the prices will be adjusted to eliminate the opportunity. Okay. Anyway, let's get into chapter 2. But before that, let's just briefly glimpse through in 5 minutes what probability 1 chapter is about. Okay, probability 1, introduction to discrete probability. Okay, here, experiment, outcomes, sample space, event, probability, or likelihood. I mean, this is cardinal sin in mathematical statistics, huh? The cardinal sin in mathematical statistics, basically probability or likelihood, not the same thing. But anyway, let's just talk about probability. Okay. So, you got finite sample space, okay? Finite probability theory. Discrete probability is referred to the probability of a finite or countably infinite sample space. Whole books have been written on the subject of discrete probability alone, exactly. But this book also covers continuous probabilities. Okay, here we have some coin toss experiments. So these are, I guess, most audience should be, or should be, I assume most audience are seen this at least once before, okay, in at least one seriously before. So, but if we encounter something that needs to be reviewed, we'll come back. Okay. Probability density function, probability space. So these are the axioms of probability. Okay. If we're being truly rigorous, the third probability should be countable additivity. This is only finite probability, but this is probably okay at this level. Just no sigma algebra. Okay. So that's completely understandable. We use this no arbitrage to derive equation. Yes, Black-Scholes was derived this way, or can be derived this way, as I remember. Well, even though arbitrages exist and quant forms do that, EMH is a conjecture, in my opinion, which could be true. I personally believe in fractal market hypothesis. Wow, okay. I've never even heard of fractal market hypothesis before. Thanks for mentioning. This is great. Yeah, it's a finite space, so that's enough. So the measurability issues are trivial. Right? So this is okay. I mean, I'm not like pointing out like inaccuracy or anything. I'm just trying to gauge the level from chapter 1. Yeah, exactly. So this is finite set, so we're okay. Probability mass function. Probability mass function describes discrete distributions. Okay, so these are most likely well understood among the viewers. Mutually exclusive events. theorem on total probability. Yeah, this is very useful. And usually theorem on total probability is used in conjecture with conditional probabilities. You would express the joint probability on the right-hand side in terms of conditional probability. We'll see if that's done in the later part of the book. Independence. This is, of course, absolutely crucial. Without independence, probability theory became analytically difficult to handle. Independence, multiple events independent. Okay, and binomial probabilities, binomial distribution. This is hugely important because when we discuss things like the option pricing, a basic model just assumes at each step it either goes up or down by a fixed amount or by a fraction. Okay, either multiply by a number or divide by a number. Okay. And here we have, okay, so this is the up, down, as I was talking about. Instead of head, tail, you have up, down. Here, this is a formula for the binomial distribution. Okay, binomial distribution. So once again, this should be pretty well-known issues. Empirical versus theoretical probability. So this is some sort of long-run frequency, right? Empirical probability. Random variable. Random variable is a function. It's a measurable function. Okay, and indicator function. I'm working on a video on sampling survey right now, and it should be out, well, if not today, but tomorrow, and makes extensive use of indicator random variable. This is such an unassuming tool. Indicator function is such an unassuming tool, but it's actually very, very useful. It lets you, even not only it is a defining tool in, say, Lebesgue theory, in measure theory, it's a defining tool in measure theory, but in practical calculation, indicator function sometimes allows you to simplify calculations a lot, especially when it comes to bypassing complicated combinatorics. Okay. Indicator function, very, very useful stuff. Anyway, let's keep going. Probability distribution of random variable. Okay, that's cool. Probability mass function. Yeah, probability mass function of the discrete random variable is now defined. And also have a random vector. Instead of a real valued, you have Rn valued random variable. Okay, this R valued is called classic random variable. But of course, you can have multiple components in the value of x. Okay, and independence of random variables. Now, before we talk about independence of event, here we look at independence of event. Here we have independence of random variables. Once again, this is random variables that are discrete. And this definition only works for discrete random variables. Expected value. Expected value, mean, and here we're only dealing with finite sums. So no issues of convergence occurs here. That's cool. Expectation, the expectation function is linear. EMH basically at the end says the market is a random walk. This is disagreed by many mathematicians as the true Brownian motion has Hurst exponent to be. Okay, I see. So it's rougher, huh? It's rougher than Brownian motion. You mean the Hurst exponent? Is that the Holder? Is this the same as the Holder exponent? Hurst exponent? Is this the same as Holder exponent? Yeah, I know Brownian motion should be 0.5. Yeah, I know. But so the market is the power trading is. Does that mean the market is more rough than BM? I respect a strong independent variable. Leo Lecter. Thank you very much for joining the stream, Leo. Yeah. So here we just look at the definition of the expectation, and immediately we have linearity. This is perhaps the most important property in the usage of all in all usage of expectation, linearity. Holder, yeah, I was thinking of a Holder exponent, but perhaps that's something else, right? This is different, perhaps. No. So anyway, here, expected value of a functional random variable. Yeah, so once again, this is very similar to the definition, even though this is not the definition. This is sometimes called the law of unconscious statistician. These two formulas are sometimes called the law of unconscious statistician because allegedly statisticians regarded these as definition of expectation, which is not true. So this is of course this is hugely offensive towards statisticians, and I might consider myself one, but I'm not offended. Okay. Okay. Yeah, 0.1 means market is more volatile. Okay, I get it. So perhaps use fractional Brownian motion, huh? Yeah, Leo says, if you have three pairwise independent Bernoulli but not fully independent, and one gets that three-way mutual information and the variable is negative. Yeah, so Leo actually mentioned something very important, which is also mentioned in the book. Independence is very strong. Independence is a very strong assumption. Okay, so even if you have pairwise independence, you don't necessarily have full independence. I made a quiz about that long ago. I mean, not so long ago, like a month or so. But basically, here, you see, this is a definition of independence. Let's read it a bit more carefully. If you have a collection of events, okay, let's say this is just a finite collection of events. We call it independent if for any subcollection, EI1 all the way to EIK, now any subcollection of these events, we can have this factorization of joint probability. Note that to check whether or not three events A, B, C are independent, we must check three conditions. Hang on. That's not enough? Damn, this is not enough. What? The book is wrong, huh? Note that to check whether or not three events A, B, C are independent, this is only pairwise independence. This does not guarantee full independence. Oftentimes in cryptography and complexity, we get away with just pairwise. This is not full independence. I mean, we must check three conditions. These are of course, these are necessary but not sufficient, huh? What the hell? Okay. I mean, I'm not trying to criticize the author here, but this is a mistake. Which is okay. Everybody makes mistake. There's no shame. Okay, there's no shame. But I think this is perhaps worth pointing out because a beginner might easily get confused here. BTFO. Okay, I'm not quite well versed in internet slangs, but this is a mistake. Okay, this is perhaps an oversight. Sorry. What's that? Something that is innocent mistake. Okay, but let's just point out that this is not true. This is not true. Let's. I made a a quiz a long time ago. It's difficult to find it at the moment because the community post. The community tab post. Okay, so basically, it does not have a very good feature for searching my past posts. That's unfortunate. Yeah, the definition is correct. Why is it wrong? Because the definition is correct. Any subcollection, this must include any subcollection which here, if you have three events, then you must have A, B, C together are independent. So you need the joint probability of three events to factorize to. Yeah, maybe just an arrow slip. That's what I thought. Okay. A professor in mathematics cannot possibly not know this. So let me just go to. It's difficult to do searches in my community tab, which is annoying. But basically, I think that happened. I made the question like a month ago, before the channel got hacked, if I recall correctly. So let me just do that. If I cannot find it in 2 minutes, I'll just skip. Yeah, actually here, thank goodness, I found it a month ago. So here you can see, this is, let's put it side by side. Here, this is the question. Probability quiz, true or false? Let A, B, C be events if, actually, I wrote if the three events, if the joint events A, B, C can factorize, then A, B, C are independent. If they're pairwise independent, all three are independent, no. I don't think so. I don't think so. If you can, does the independence at level 2 implies independence at level 3? Probably not, huh? Actually, this is a different question, right? I'm glad that I went through the quiz here. The majority of people realize this is false, so that's good. And here's a counterexample. Is this correct? If you have pairwise independence, then the whole thing must be independent. Is that true? AB, AC, and BC. I don't think so. Thoughts in chat? Can we create a counterexample on the spot? We do something analogous to Kun. Yeah. Yeah, I just want to have something elementary because this is very important. I'm glad that somebody brought up this issue. I think Leo did. So the goal is, can we create okay ABC that are pairwise independent, but the factorization at the 3 level failed. Okay, I'm trying to figure something out. Get some numbers. A, B, and C. So here, guys, yeah, the factorization will fail with the coin flip. I think so. So let's just give an example. Example. Events A, B, and C that are mutually independent but aren't independent. Okay, and this is the construction. So I think this should work. So let's take a big omega to be head tail squared. Okay, so that's the outcome of tossing 2 coins or tossing the coin twice. So head head, head tail, tail head, and tail tail. So you have this set omega here, and let's assume the coins are all fair. So define the events. Let's define the ABCs here. A is the event. First toss is head. First toss is head. So A is head head, head tail. 2 outcomes. And B is second toss is head. Second toss is head. You have head head, tail head. And C is 2 tosses have the same result. 2 tosses are same. So it's either head head or tail tail. So let's calculate a bunch of stuff. Okay, so then we have PA. Of course, PA is 1/2. 2/4, which is 1/2. And PB, PC are also 1/2. Okay, let's look at the joint events with 2 events taking intersections. Okay, A intersect B. Well, A intersect B is just head head. Single element, head head. So that's 1/4. As you can see, this is PA times PP. So that's good. That's what we wanted. PA intersect C. Intersect C once again is head head. PA times PC. So that's good. And CB, BC. BC is head head too. PBBC. And now let's look at the 3 level. is head-head. So once again, it's one force again, but it's not PA times PB, PBC, PC. Okay, so that's the counterexample. So the moral of the story is mutual independence does not imply full independence. Leo says, exercises for chat show that with n events, you can have m minus way independence, but not full independence. Slightly harder show that you can have k way independence for each k less than n. But as soon as you get to k plus 1, they're not independence anymore. Good exercise. Can we do that perhaps using induction? I'll make a screenshot. Okay? Thank you very much, Leo. And put it here. Okay. Just so this question is not forgotten. Okay. So anyway, let's get back to the main topic. Okay, so that's cool. That's cool. We managed to call a little mistake here in the book. Okay. Anyway, here let's continue. We have what's D? What's this D here? Oh, it's a specific example. Okay, it's not a special notation. Where were we? Independence of random variable. We've seen that. Expectation. We've seen that. Yeah, variance and standard deviation. Now, it's a definition of variance. Expected value of x minus the mean squared, which is also the minimized mean square error. Right? Remember, we've been hammering this point on the channel. Whenever you see mean and variance, think of a right triangle. Random variable x. This is a straight line. Straight line is a span of 1. Span of 1 means the set of all constant functions or degenerate random variables. Okay, then this is mu or ex. And the other leg of the right triangle is the standard deviation or the square root of the variance. Yeah, to be honest, that's a pretty important mistake. Yeah, it's not. Yeah, it is a pretty important. I agree, especially right under the definition of independence. But it's an easy mistake to make. Subtle stuff. Indeed. Yeah. Hopefully now we're clear. Okay. I was in shock because, well, right after, except for that exact reason, right after the definition of independence. Anyway, let's keep going. Here you have some properties of the variance and standard deviation, in particular the third one. This is a Pythagorean theorem. This is a Pythagorean theorem for variance. Okay, and here also linear combinations of variance is not the linear variance of linear combination is not linear combination of variance. This is very important. If that's true, then you can pick B and A to be opposite sign and cancel out variance. Of course, it doesn't work that way, right? Expected value of a binomial random variables. This is a well-known formula. NP times 1 minus P. Okay. We leave the derivation of the variance as an exercise. But the thing is I'm not sure if that's fair because the derivation of variance needs a trick. The derivation of the variance very much needs a trick. Okay, but that's fine. Covariance of correlation, best linear predictor. This is perhaps important. Let's take a look at the best linear predictor. I assume people have seen. I'm the guy who requested the stream. Thank you very much. Oh, yeah, Civil. I remember it. I remember you. Yeah. So here, I think it's perhaps important that we spend a little bit more time. Okay, I spent well over 5 minutes. I apologize on chapter 1, but yeah, we managed to caught a mistake in the book, so that counts. Okay, so that's worth it. On independence, we have a Leo surplus in the stream. Yeah, it's a very popular name. Here we have covariance and correlation. Okay. The covariance is defined as the expectation or expected value of x minus mu x times y minus mu y. Yeah, I remember having done this mistake in the past. Apparently, I keep forgetting it because it's counterintuitive. Exactly. Yeah, no worries. The top coder, thank you very much. Okay, so once again, we're introduced to a new concept, well, in the book at least, called covariance. And immediately we have a bunch of properties. The first one, the formula, covariance of x and y, which is expected value of x times y minus expected value of x times expected value of y, is directly available from the definition of covariance by the linearity of E. Now you can just expand the product and you'll get this formula very quickly. So I'll skip that, okay? But be sure to show this formula from the definition if you've never done that before. Symmetry. Well, symmetry is obvious because the product is symmetric. Yeah, covariance is also important bilinear form. You're totally correct. You're totally correct. It is a bilinear form. Do we have that statement here? Now we'll get to that probably. Covariance of x is just the variance of x. Exactly. X with itself is just the variance of x. If x is constant random variable, if sigma x is 0, then it equals 0. Yeah. If x is a constant random variable, it must equal to its mean. So the product vanishes. So that's why. Yeah, this is what Leo was talking about. Bilinear form. Here in point 5, the formula is linear in its first argument, but because covariance is symmetric, right, you get the linearity in the second argument too. This is a bilinear form. 6, the covariance is bounded by the product of standard deviation. This is the Cauchy-Schwarz inequality. This is the Cauchy-Schwarz inequality. Moreover, the equality holds if and only if either one of x and y is constant. Yeah. Or if there exists constant a and b for which y is a perfectly linear function of x. Or if we're being super pedantic, we'll call it the affine function because you can plus a constant. Okay. So this holds with probability 1. If this holds with probability 1, then the equality in the Cauchy-Schwarz inequality hold. Okay, once again, shameless self-promotion. I posted a quiz a while ago asking this. Is the covariance an inner product? Is on the space of L2 random variables, is covariance an inner product? This is a nice overlap between probability and linear algebra, if I do say so myself. Is the covariance an inner product? The answer is no. It is almost an inner product. Because of what? Because 4. Because of, actually, this should be covariance of x and x. Here's a little typo here. So basically, because of 4, covariance is not an inner product. Inner product requires a definite property or definite axiom. Yeah, it degenerates, that's why. Because there's a property in inner product. Let me just put it on the side. Okay, so what is the inner product? Recall, inner product definition. Let V angle bracket be a real inner product space, then you can easily look this up in Axler. But basically, these are the axioms. Be a real inner product space. Or should say, no. This is a real inner product space. If V is a real vector space, and the angle bracket satisfies the following properties, called the inner product axiom. First, you have positivity. So for all x in V, the inner product of x and x is greater or equal to 0. So that's positivity. Second, you need the definiteness. It says if x and x inner product is 0, then x must be 0. And that violates, so 4 violates this one. This is a definite property. 3, okay, 3 is what? 3 is symmetry. xy inner product equals yx inner product. It's not a typo. It's not a typo. It's just the right property. Exactly, you're right. Exactly, you're right. You are completely right. You are completely right. So it's not a typo. You just need one of them. You just need one of them to have 0 standard deviation. So basically, I'll try to I'll write down what exactly makes the covariance not a inner product very soon. Now, this is symmetry. And lastly, you have linearity in the first position. Okay. Ax plus by inner product with z equals a inner product xz plus b inner product yz. So holding the second argument constant, the function is linear in the first argument. So that's the inner product space. Covariance is not. Covariance xy satisfies 1, 3, 4, but not 2. But not 2. So this is important. Basically, definiteness, as we can see, the variance of x equals the covariance of x and x equals 0 implies x is constant, not necessarily 0. Okay. Definiteness, as we can see, does not affect Cauchy-Schwarz inequality. So Cauchy-Schwarz inequality is a property of symmetric bilinear form, symmetric and positive definite. Actually, not definite, symmetric positive. Cauchy-Schwarz inequality, you just need bilinearity, symmetry, and positivity. You don't need definiteness. So Cauchy-Schwarz inequality does not rely on definiteness. However, the definiteness property is useful for defining orthogonal projection. Things like this. If you don't have definiteness, then orthogonal projection is not even a well-defined operation. Okay. If you don't have definiteness, it turns out that orthogonal projection is not unique. So therefore, we require definiteness because so much of our geometric intuition relies on uniqueness, existence and uniqueness of orthogonal projection. Okay, that's why it is here. Once again, these are issues that are discussed in the short quizzes on the community tab. Because I feel like these issues are important, but they don't warrant a full-length video. Because you know, people don't have time to watch like a 5 minute video for such a small but subtle thing, right? So you just do like a 10-second quiz and see if you got it right. That's my approach of doing things. If you don't have definite, you feel insecure and end up being less confident. Very important. Yeah, orthogonal projection feels very insecure. Right? Orthogonal projection relies on definiteness. Otherwise, it's not even a well-defined function. Okay, so that's why we mentioned this little subtlety here. Even though covariance very much behaves like an inner product, it is not quite. Okay, it's not quite, and not literally a or not literally an inner product. Okay, so here this is a classic proof of Cauchy-Schwarz, totally unmotivated, totally unmotivated. You have to just memorize the proof. You construct a quadratic function basically. 10-second amateur hour takes me two. Well, it's an exaggeration anyway. So yeah, typically I think the quizzes on the channel requires about like a minute or so, if you've never seen it, to think carefully to get an answer. For example, I mean, if you like for example today's quiz, if you yeah, what's today's quiz? It's on linear algebra, right? Like if you've seen, oh wow, 32%. What's going on? You just is it? Are you serious? 36%. Huh. If two matrices have same characteristic polynomial, they must be similar. Only 36% got it right? Wow. Once again, if you've seen Jordan form, then this is trivial. If you've seen Jordan canonical form, this is trivial. If you've seen Jordan canonical form, it takes you 2 seconds. But if not, it probably takes like a minute or whatnot to get it right. Wow. I'm actually totally surprised by this result. I know yesterday's result is, well, you see, this is yesterday's quiz. It's probably a matter of forgetting the exact definition. But this is a big mistake, huh? Yeah. Anyway, let's continue. It's not a linear algebra lecture. Correlation coefficient. You see, correlation coefficient relies on Cauchy-Schwarz. Because without the Cauchy-Schwarz, rho cannot be bounded by -1 and 1. So that's correlation coefficient, which is once again very important in CAP-M model. I was going to do all the quizzes on stream maybe tomorrow. Now Ming's giving all the answers out. Okay. Anyway, okay, I'll stop talking about my quizzes. Okay, sorry, Leo. Um, um, anyway, so here we have some more terminologies: perfectly correlated, perfectly negatively correlated. So this means x and y has a perfect linear relationship with probability 1. However, it is still possible to have uncorrelated random variables that are dependent. It is totally possible to have correlated random variables that are dependent. Let's think about an example. Perhaps this is worth doing because the book didn't put it in the text. So let's give an example that random variables that are correlated but uncorrelated but independent. Example. Random variables that are, I've seen people with live automatic subtitles. I don't know how to enable it. I don't know. I don't know. Hi Nadia. So here we have that are uncorrelated. That's what I'm trying to give an counterexample of. But not independent. but not independent. Okay, so here's a simple example. Let x be a discrete random variable that takes values -1, 0, and 1. And the probabilities are 1/3 each. Okay, this is x, and define y to be x squared. Define y to be x squared, so let's first show that they are uncorrelated. You just need to show the covariance of x and y is 0. Then the covariance of x and y, let's use the formula, expected value of x times y minus expected value of x times expected value of y. Well, that's just the expected value of x cubed. But remember, x is symmetric about 0, so x cubed has 0 mean. And so is x itself. So this is just 0. Therefore, x and y are indeed uncorrelated. The covariance is 0. Y equals x squared, this means they are obviously not independent, but we can give a formal argument as well. Well, you can just, of course, the heuristic is, oh, y is a function of x, they cannot be independent. But let's be a little bit formal. To do so, let's look at the joint distribution. You should always be prepared to give the actual formal argument. Okay, so y takes values in 0 and 1. Okay, but because there is a relation, the fixed relation, deterministic relation between y and x, then only certain entries are non-zero. X equals 0, y equals 0, that's a non-zero. And this is a non-zero. It's just right, not 0. Okay, not equal 0. The probability is not equal to 0. Okay, so here the table is meant to represent joint probability. And I don't need the exact value. Okay, I just need to figure out which ones are 0, which ones are not. X equals -1, y equals 1, that's a non-zero probability. X equals 1, y equals 1, that's a non-zero probability. Everywhere else, the 3 other entries are all zeros. Okay, so therefore we can get a counterexample. The probability of x equals -1, y equals 0 is 0, which is not the same as probability of x equals -1 times probability of y equals 0. And just to be concrete, let's figure out the product. X equals -1 has a probability of 1/3. Y equals 0 has a probability, well, y equals 0, that means x equals 0, so that's another 1/3. So this is a full counterexample of random variables that are uncorrelated but not independent. Because here y and x satisfy a nonlinear function. Right? You can think of correlation is only effective in detecting linear dependency. Okay, so here we have no linear component at all. It's just purely nonlinear. X squared is purely nonlinear. There, I was thinking the Taylor expansion around the Taylor expansion of x squared around the mean of x has no linear component. That's what I'm trying to say. Like this example, just yeah. So very classic example. Introductory probability course should always mention this. Uncorrelated random variables are necessarily independent, and of course, independence implies uncorrelatedness. It's no correlation basically. So we will have much use for these terms during our study for portfolio management. Exactly, that's why we're spending time on it. Oh, best linear predictor. This is interesting because this has to do with the geometry of statistics we've been doing on the channel. Let us examine the meaning of correlation coefficient more closely. It is often said that the correlation coefficient is a measure of the linear relationship between x and y. Okay, so this is a linear relationship. We just saw how important the qualification linear is. Indeed, which I have just said, perfect correlation is equivalent to a perfect linear relationship between random variables. To explore this further, suppose we wish to approximate y using some linear function, beta x plus alpha of x. Okay, this is a little bit different than linear regression, a little bit different than the classic linear regression model. Why? Well, a little bit different, but not so different. It's because in classic linear regression model, x is treated as not a random variable, but as a constant, basically part of the parameter. Right? It's part of a parameter for the distribution of y. Okay, so here we're using interpretation that both x and y are random. Somebody dig up Gaussian Markov. Exactly. Yeah, so you're talking about the optimality result called the Gauss-Markov theorem. Blue. Christian was talking about the best linear predictor. Best linear unbiased estimator. That's blue. Unbiased is important because if you remove bias, if you introduce bias, then you can get a smaller variance actually. Yeah, estimator is Gauss-Markov theorem. So Gauss proved it under the assumption of, well, Gaussian distribution. Markov showed that the Gaussian distribution assumption is not necessary. You just need constant variance and uncorrelated residuals. It's a good exercise in linear algebra. I'm going to type it in chat. Blue. So here, the error in this approximation, epsilon, is y minus beta x minus alpha. It's called the residual random variable. The best fit is generally considered to be the best linear predictor that minimizes the mean square error. Yeah. So that's the objective here. Wish to minimize the mean square error, minimize MSE. Okay. So of course, the algebraic way of doing such minimization is simply expanding the function, and you instantly recognize, oh, this is a function of alpha and beta. This is a quadratic function, alpha and beta, and you can use the first order condition in calculus to set up a system of equations, a system of linear equations, in fact. Okay, and you get these results. So let's do that. Okay, this is very much in the same spirit of portfolio optimization, actually. So let's do the algebra here. Okay, as we should verify this. Let's first do the algebra way, and then do a more geometric way, or linear algebraic way. So you get random variables x and y. Let me just start the topic here. Best linear predictor. BLP. Okay, let x and y be random variables. We wish to choose constants alpha and beta such that the MSE, which is a function, let's just call it, does it have a name? Does the function have a name? No, it doesn't. Let's just give it a name. Let's call it Q because it's quadratic. Okay, Q alpha beta defined as the expected value of epsilon squared, which is the same as the expected value of y minus beta x minus alpha squared. Okay, so this is MSE. Let's expand. And expand and use linearity. So this is our solution. Q alpha beta, you expand the product inside the expectation, you get y squared minus, let's put all the square terms first, y squared plus beta squared x squared plus alpha squared, and all the cross terms, which is 2 beta xy minus 2 alpha y. Okay, and then plus alpha squared. Oh, sorry, not alpha squared, but minus, plus 2 alpha beta x. All right. Bye, Leo. Thank you very much for joining the stream. Thank you very much. Okay, so here, let's take a look at the algebra. So here we have a quadratic function, alpha squared plus beta squared times the expected value of x squared. Why don't we just keep things in order? Because this is perhaps not the best way to avoid being confused. Keep things in order, okay? I don't know why I did that. Sometimes I randomly shuffle things and end up confusing myself. Okay, so the first term is a constant. And then you have beta squared x squared taking expectation, that's right, and plus alpha squared. Minus 2 beta expected value of x times y minus 2 alpha expected value of y plus 2 alpha beta expected value of x. Right, so this is the quadratic function, and let's do the partial differentiation, dq d alpha. This is unconstrained optimization. dq d alpha gives you 2 alpha minus 2 ey, and last term 2 beta ex. Okay, second partial, the other partial derivative, dq d beta, is 2 beta ex squared, 2 beta ex squared, alpha squared cancels, minus 2exy, 2exy, and finally the last term is plus 2 alpha ex. So you need to set them to be 0. Both be 0. Okay, so once you have that, you get the so-called normal equations. These are so-called normal equations. Normal in the sense of not normal distribution, but perpendicular. Normal means perpendicular because this is fundamentally a geometric relation, as we shall see after this derivation. Okay, so you have this system of linear equation. Let's maybe put that in the matrix form, shall we? First of all the 2 cancels out. Let's put it in the matrix form. Alpha beta as our column vector of unknowns. 1 ex 2 by 2 matrix. 1 ex, right hand side is ey. Here in the second row you have ex here, yeah, ex squared here, and on the right you have e of x and y. So this is the matrix, This is a matrix. So let's solve that. Use the 2 by 2 inverse matrix formula, okay, which I will write it on the side. So if you have A, B, C, D, assuming invertible, then the inverse would be 1 over the determinant times D minus B minus C and A. Right? You swap the entries in the main diagonal on the main diagonal, and you put a minus sign on the off diagonal elements. So here alpha beta, let's do the calculation, is 1 EX EX. Oh, thank you very much. EX squared. This is regression where x and y are purely random as opposed to yes. This is regression. This is actually the original regression by Galton, Francis Galton. Galton's regression to the mean. This is OG regression. Deming regression, I think it's called. I'm not sure. I think this is, yeah. This is called regression to the mean by Galton. Galton, of course, is very famous statistician and eugenicist. Which is now discredited theory, I mean, eugenics. So anyway, so let's calculate the inverse matrix. 1 over determinant expected value of x squared minus EX squared. Okay, and then you get EX squared minus EX here and 1. Elon Musk, Galton's best idea. Yeah, I know, right? Okay. So as we can see here, immediately we recognize this is nothing but the variance of x. So let's write that as sigma x squared. So you got 1 over sigma x squared. Matrix multiplication gives you a vector which is EX squared, E of x squared times E of y minus E of x times EX EY. EX E of xy. Doesn't look like you can simplify further. That seems to be it. All right, so then we do the second entry, and that turns out to be just EXY, E of x and y minus EX times EY. Okay, so what do we have here? Well, the first entry is a little bit difficult to interpret. But the second entry, this is just covariance. This is just the covariance of x and y, which by our definition of correlation coefficient is exactly rho xy times sigma x times sigma y. And that's the second entry, right? So therefore we conclude beta. Okay, so beta is rho sigma x and y. One sigma x, or one of the sigma x cancel, so it's rho x and y times sigma x, times sigma y over sigma x. So this is beta. Okay, this is our solution. Let's compare with what the book says. Yeah, this is correct. Right, so sigma x and y, this is the covariance. Covariance divided by variance of x squared. So that's another form. That's another form. So alpha is not given, or we're not given a alpha. We're not here. Alpha is not in an explicit formula, but rather just a rearranged second equation. So yeah, so this is beta also equivalent to the covariance of x and y over the variance of x. And alpha is simply here, the second equation. Alpha, this one, alpha is simply ey minus beta ex. So this is saying, this sentence is saying the fitted line, sometimes also called the least square line, y equals beta x plus alpha, passes through the point ex, ey. So those two statements are equivalent. So this finishes the algebraic side of the story. But of course, on this channel we would like to do things geometrically. On this channel we like to do things geometrically. So how do we interpret things geometrically? Geometric picture, geometry, geometric interpretation. Remember, x and y are just L2 random variables. In practice, you would start calculating beta, so it makes sense to express yes, yes, yes. That's right. Well, in practice, I'm pretty sure nowadays you just use matrices and get all the entries at the same step. But I think most calculators do it this way, right? Most calculators do it beta first and then alpha. And this beta has applications in cap M. This leads to the beta in cap M. So the geometric interpretation is also very clear. So L2 is a big vector space. Right? So yeah, L2 is a big vector space, and x and y are vectors, random variables which are vectors in this vector space. So what we want is the following. So we want to approximate y by a function which is beta x plus alpha. You can think of it as beta x plus alpha times 1. And that lives in the span of 1 and x. So that's the picture here. So imagine the ambient vector space is L2. And here you have the span of 1 and x. Which can be visualized as a plane. Y, of course, does not necessarily lie in that plane, because if that's the case, then y equals beta x plus alpha with probability 1. So in general, y is not in the span. Okay. What you do is to minimize the distance is equivalent to minimizing over alpha beta. MSE is equivalent of orthogonal projection onto the span. What apps does the sort of stuff like MATLAB? A lot of stuff, like Excel does it, right? Now, of course, MATLAB does it too. MATLABs are exceptional when it comes to handling matrices. 2x2 matrices are a piece of cake, right? Literally all calculators. This is linear regression is a feature in most calculators, in most calculators with statistic features, I believe. So, yeah, linear regression between two variables. Minimizing the MSE is equivalent of orthogonal projection. Orthogonal projection onto the span of 1x. So that's the geometry here, L2 geometry. Yeah, if we want to do any kind of statistical model theory, R is a good language. Yeah, I know. R is a good language for statistics, but this is mathematical finance, right? Mathematical finance, but perhaps old school mathematical finance just use Excel. A lot of data are this sort of features are. I mean, R gives you more customizability. You can create your own algorithm. A good place to start is just Excel. So here you have, this is y hat, okay? This is y hat, the approximation. Y hat is the BLP. So that's the geometry. Because everything in that space has that form. So how can we get to the normal equation? How can we get to the normal equation? Well, y equals the BLP if and only if y minus y hat, that's the residual, is perpendicular to the span of 1 and x. Right? Assuming that x is non-degenerate, this is equivalent of y minus y hat perpendicular to 1 and y minus y hat perpendicular to x. And what is perpendicularity in L2? Remember, in L2, x and y in a product is defined as expected value of x times y. This is obviously in the product. Right? This is obviously in the product, so therefore you get the expected value of y minus y hat equals 0 times 1. Right? Y minus y hat times 1 equals 0. And expected value of y minus y hat times x equals 0. And so that's it. These are the normal equations. So these are the normal equations. So expand, you get expected value of y equals expected value of y hat, and expected value of x times y equals expected value of x times y hat. And now you can use y hat, the form of y hat. Y hat lives in the space, lives in the subspace spanned by 1 and x, so y hat is beta x plus 1. So y is, use linearity again, beta times ex. Oh, sorry, plus, not plus 1, plus alpha. My bad. Use linearity to expand, you get beta times expected value of x plus alpha. Expected value of x times y equals beta expected value of x times a square, okay? Square, and then plus alpha expected value of x. See, this is a normal equation, which is exactly the same as we got from partial differentiation. Same thing. Normal equation, as you can see. The normal equation means perpendicularity, geometric interpretation. Okay, so that's the best linear predictor. I think we can go on now. Definition: let x and y be random variables. Write y equals beta x plus alpha plus epsilon, where alpha and beta are constant, and epsilon is a random variable defined by y minus beta x minus alpha. Then y is approximated by the linear function beta x plus alpha with error, random variable epsilon. The best linear predictor of y with respect to x, denoted by BLP, is a linear function beta x plus alpha that minimizes the mean square error. That was a good 5-minute overview, I know. I know. My goodness. But I mean, we're not wasting our time, because here we will come back to this. Because when we do cap m, we will come back to this for sure. Because I cannot just, I'm just going to quote this formula. Right? So we're paying the cost up front. Okay. Moreover, the minimum mean square error is this one. Actually, you know what? Let's verify that. We derived the BLP. Let's verify the mean square error, the actual mean square error. Okay. You just substitute into this mess, I guess. Is there a good way to do that? Is there a good way other than just brute force substitution? Of course, you have alpha and beta. Can you just plug in and simplify this mess? Is there a good way to do this? Preferably geometrically. I'm not quite sure. Does it have a geometric meaning? Okay. So the minimum over alpha beta of the MSE is, the minimum is sigma y squared 1 minus rho squared. Can we interpret this geometrically? Remember, rho is like a cosine, right? So this is sine square. This is probably a sine square, but we need to specify what the angle is, right? And sigma y squared is, well, let's draw the picture a bit more carefully. Use the mean variance right triangle. Okay, so let's do things a little bit more carefully. So here we have, probably you can do this geometrically, I think. It looks strongly geometric. So okay, so here this is the span of 1. This is span of 1. Here we also have, let's say this is y. This is y, okay? This is the orthogonal projection of y onto the span of 1. And the perpendicular component, using our right triangle, here, the perpendicular component is exactly the standard deviation. So that means the perpendicular component, this is sigma y. What is the minimized MSE? The minimized MSE is the square length of this thing, right? So this is, imagine this is y hat. This is y hat. And that minimizes the distance. So basically, you project y onto the plane, you get y hat. This is y hat. So this is the square root of MSE. Let's just put it here. Square root of minimized MSE. Square root of the minimized, let's put a m, big M. Minimize MSE. Okay? So obviously you should have a right triangle here. The dotted lines form a right triangle. Sigma y is the hypotenuse. right? So the angle is this one. This is the angle. This is theta. This is theta. So the square root of this is equivalent of saying the square root of the minimized MSE is sigma y times sine of theta. I was thinking of this as a sine. Right? This is a sine of theta. Does that make sense though? Does that make sense? Somehow we never even used x. You see, somehow we never even use x. How come? Well, x is implicit because x and y determines the plane. So why don't we just draw x on the plane to see what's going on here? So imagine this is x. Okay, so what exactly is the angle that corresponds to the rho? Because rho is some sort of cosine, remember. Rho is some sort of cosine. So rho xy, remember, is defined as covariance of x and y over sigma x, sigma y. So when you do covariance and standard deviation, you are using this centralized or centered random variable. So that's the inner product of x minus mu x, y minus mu y over what? Over the, hang on, this is the sigma x, so you get, so basically that's the length of x minus mu x times y minus mu y. So we need to do another orthogonal projection of x onto 1. Let's do that. So by the way, this is how the geometry of statistic videos are made. I was looking at the formulas and trying to figure out the geometric interpretation. Okay, and once I figure that out, I'll put it in a video and draw a nicer picture in PowerPoint. So the angle, what we're talking about is this vector, is this vector and this vector. And indeed, that's correct. This is a horrible picture because here, this one and this one should be perpendicular. This and this should be parallel. Okay, these two should be parallel. These two should be parallel. Actually, you know what? Let me redraw it. Let me redraw it. So this is a geometry. Okay. Here you also have perpendicular here. This is perhaps not obvious. Let's prove that real quick. So, this vector right here is, this part is y minus mu y. This point is, it means this is 0. So this is y minus mu y. Y minus mu y minus y hat. Is it perpendicular to 1? Let's calculate. Expected value of y minus mu y minus y hat times 1. This should be 0. But let's check. This is ey minus mu y minus ey hat. Okay, minus y hat. So hang on. This should be no. They are they perpendicular? Is this perpendicular to one? No, that would mean EY hat is 0, no? It's not. It's not. What we need is this segment is perpendicular to this segment. So this is actually what we need. Because here theta in the formula theta, the angle theta, let me just write that. Theta is the angle made between the vector mu y minus y. This is mu y minus y. This is mu y minus y. And this part, which is, this part is hang on, actually, this part is, no, this part is, I think I made a mistake here. This green line segment or vector should be mu y minus y hat. There's no y hat here. Mu y minus y hat. So we just need to check whether mu y minus y hat. This is mu. This point is mu y, not y minus mu y. This point is mu y. Okay, mu y minus y hat. Just need to check the perpendicularity of mu y hat, mu y minus y hat, and 1. If that's done, then we're good. Gotta leave. Thank you, Christian. And so unfortunately, we haven't got into the cap M. We'll do a makeup stream if we cannot do it, because I don't want to rush over stuff. Okay. We will, if we can't get into the main definition of cap M, we will do a makeup stream next week. So here we have the calculation of expected value of mu y minus mu hat. Can we expand? Yeah, so expanding that, you get mu y minus the expected value of y hat. Y hat is beta hat x plus alpha hat, okay, which is mu y minus ex beta hat, ex times beta hat minus alpha hat. Right, so let's use the formulas. This is 0, right? This is 0 because mu y. Yeah, this is 0 because of the second equation already. Ey equals beta ex alpha. So this is just 0. So you're done. Indeed, this is perpendicular. Indeed, so we're good. So basically, this is the geometric meaning of the formula. This is the geometric meaning of the formula. So this is sigma y times sine of theta. minimized the MSE, taking square root. Everything is in this right triangle. 1 minus rho squared is indeed a sine square. So everything happens in, oh, this is a terrible color. Let me draw, use a perhaps lighter color than this one. Yeah, let's use this one. Everything happens in this right triangle here. That's the geometric meaning. You guys are in the channel probably because you guys like the geometry of statistics. So here's one. Theta is the angle between mu y minus y, yeah, and mu y minus y hat. That's the meaning here. Okay? Cool. Let's move on. It is worth mentioning that a strong correlation does not imply a causal relationship. Of course, correlation does not imply causation. The variance of a sum. Oh, by the way, this is important. Variance of a sum, because at the end of the day, we wish to minimize the variance of a portfolio, right? You can think of a portfolio as a linear combination. The value of a portfolio is a linear combination of its components. And you want to minimize the variance of a sum. So, and this is what you get. You just use bilinearity and expand. That's it. You just use bilinearity. You write the variance as a covariance with itself and use bilinearity to expand. And this, by the way, can be written in matrix form. So let's write that. Okay. The variance of a sum, or more appropriately, variance of a linear combination. Variance of linear combination. So the variance of the sum of alpha ai xi I from 1 to n is just the covariance with itself. Okay, so for simplicity, I'll omit the index, just write sigma. AI, actually, I put a one index. Okay, I will not write the bond, just sum of I. AI xi, sum of aj, xj. Right, and use linearity, you get the sum of ij, sum of I, sum over j, ai, aj, the covariance of xi, xj. And this can be written in matrix form, which is A transpose sigma. Should I use sigma? Yeah, let's use sigma, even though it is, okay, I'll just try to differentiate this with the sum of A. This is what we call a quadratic form. Bilinearity, exactly. Here use bilinearity. Where A is A1 all the way to AN transpose, and the ij entry of sigma is the covariance of xi, xj. Okay, so this is called the variance covariance matrix, or covariance matrix. A top trader, is a top trader, a guy, a top coder, somebody corrected me on the efficient market hypothesis. I forgot his name. Power trading. Yeah, power trading. Yeah, he was referring to this matrix, variance covariance matrix, or just covariance matrix. The reason it's called the variance covariance matrix is because the diagonals, if you have ij's, are the same. The diagonals are variances. Okay, for example, 2 by 2, sigma looks like this. Covariance of x1 and x1, which is just the variance of x1. And then you have covariance of x1, x2, covariance of x2 and x1, and finally the last entry being the variance of x2. Of course, due to the symmetry, the big sigma is always symmetric. And because variance is non-negative. Variance is non-negative, so sigma is a positive matrix. So it's not positive definite. We don't know about definiteness. Okay. If you have definiteness, that means no linear combination except for the trivial one has zero variance. We don't know that in general. So here we know from the definition, covariance matrix is symmetric and positive. Okay. So that's the yeah, it's by linearity and you have symmetry, exactly. It's symmetric and positive. We don't know about definiteness. Okay, this is an important formula. Okay, speaking of which, I mean, here you have exercise at the end. Okay, that's cool. We don't have time for that. Let's get into the CAPM. Okay. Hopefully we can cover the definition. Probably we don't have time to cover the option pricing today. Okay, I don't want to rush over things, but we will do the best we can when it comes to the CAPM model. In this chapter, we explore the issue of risk management or portfolio of assets. The main issue is how to balance a portfolio. So that's the objective here. How to choose the percentage by value of each asset in a portfolio so as to minimize the overall risk of a given expected return. Right? So that's the idea. But of course, this is not the full picture, right? We want to do not an unconstrained optimization, but rather a constrained optimization. So think of that this way. Given the target, which is an expected return, how do we minimize risk? Right. You have a desired expected return. So that's why you have a percentage requirement. So all the percentage should sum up to a constant. That should probably 1. And then you want to minimize the overall risk. Right. So the problem is similar to a problem in survey sampling. So basically in survey sampling, there's a similar problem. You want to allocate the sample sizes to stratas. Now, suppose your population can be divided into strata. And you do simple random sampling in each stratum. And hopefully the combined estimator have minimum variance. So this is very similar to the problem in survey sampling. Right? In survey sampling, an estimator with low variance means higher accuracy. Here, a portfolio with overall minimum variance has lower risk. And mathematically speaking, they're very, very similar. Okay, so the first lesson that we will learn is the risk of each asset in the portfolio alone does not present enough information to understand the overall risk of the entire portfolio. Exactly. While Why? Because the risk of each asset is only the diagonals of the covariance matrix. You also need the covariances. That's why. Okay. So it is necessary that we also consider how the assets interact as measured by the covariance, or equivalently the correlation of individual risks. Let's go. Portfolio. So what's a portfolio? For our model, we'll assume that there are only two time periods, initial time and final time. Okay, so that makes things easier. You basically ignore what happens in between. Right? Only care about two time periods, perhaps time instants, right? Not two time periods, but rather time instants. Each asset AI has an initial value vi naught and the final value vit. Okay, cool. So you have assets and they have values. Perhaps you can think of the value as a function, a real value function of an asset. Right? An asset in general can be, well, quite general. It can be a house, it can be a stock, well, it can even be human capital. Right? So anything that is valuable is considered an asset. And it has a function value to it. Right? So imagine V is a function, it assigns a value to each asset. Let's think of it this way. Think of it as like a random variable assigns a real value to each outcome. Here we're assigning values, literally speaking, to assets. A portfolio consists of a collection of assets, A1 all the way to AN, in a given proportion. Formally, we define a portfolio to be an order n tuple of real numbers. So that's the definition of portfolio. Okay, so let's put some notations down. Okay, cap M. Actually, you know what? Assets. First, assets. AI. AI. Okay. Initial value equals V I naught final value VIT. That's an asset. Portfolio. A portfolio is what? A portfolio formally is an n tuple. Theta I stands for the unit of asset alpha I. Okay, we allow theta I to be negative. And then this is called a short position. This is called a short position. So that's allowed here. If a short sale of a stock, a short put or call, and so on. So these are options. Put and call are options. Okay. So we allow short position in our portfolio. A positive value of theta I indicates a long position, an owner of a stock. Long or put, long on a put or call, and so on. So here we have the interpretation. So portfolio is a vector, essentially. A vector in its true sense, not just because it's an n tuple. Theta 1 all the way to theta n. Theta I positive means short on AI. Oh, actually, negative means short on AI. Positive means long on AI. Okay. Theta 1 is the unit of number of unit of A1. Theta n is the number of unit of AN. Okay, so that's a portfolio. The n tuple. Okay, so cool. So far so good. Now we have weight, asset weight. It is customary to measure the amount of an asset within a portfolio by its percentage by value. Right? This is a classic idea in applied mathematics, basically non-dimensionalization. Right? So you don't, because it's difficult to compare, say, one unit of a, well, like a house or mansion, compared to one unit of a stock, right? So let's do a dimensionless value. Right? So that's the weight of an asset in the portfolio. So of course, this is just a weighted average, WI. The weight of WI, the weight WI of an asset, AI, is a percentage of value. So let's write that down. Weight WI is defined as AI, what's the time here? Initial time. Right? Of course, you can define the initial time and for final time as well. So why don't we add a 0 at the end? I think it's appropriate to add a 0 in W as well, because we're using the initial values here. Is that AI or should be theta I? It should be theta I, yeah, theta I. A is not even a number. It might not even be a number. But theta is a percentage, so... Oh, actually, theta is not percentage, it's unit. Theta is a unit. Theta I times VI naught. And here you have sum over I. Theta I VI naught. Okay, so that's the weight. Initial weight. Of AI in the portfolio. So, these are the fundamental definitions. Let's keep going. Sorry, why is just 2 times initial? Why just 2 times? I think it's a simplification, because we don't want to discuss stochastic process yet. There's no time evolution here. Okay, so this is just the setup. Okay, to simplify matters, I suppose. Because once you have this simplified setup, you can then talk about a sequence, like a discrete time stochastic process, right? At each step, what happens? I think that's the idea. First you just do, I think this is just one period. This is not 2 periods, it's just 1 period. And then in subsequent chapters, you can talk about a multiple period. Then you have a time evolution. Eventually, you want to get into continuous time. And I think this is the order I will go about in the stochastic series as well. So you just use 2 time instances to illustrate the idea. Is he reading Green Book? What is the Green Book? This is just a... This is not a green... I don't know what Green Book you're talking about, but the link of the book is in the stream description. Yeah, simpler case to complicate later on. Exactly, that's exactly why. Because right now, if you want to discuss time evolution, things are there's too many variables. Okay, so the sum of WI is always 1, clearly. And now we want to talk about returns. Okay, so return is defined in a straightforward manner. It's just the amount you gain by the end of the period divided by the principal, essentially. Now this is Ri. I assume you only consider VIT to be random. The initial amount should be fixed. Okay, should at least be known. So that's the return I. Return I, of course, is dimensionless. It's a percentage. You can think of it as the interest rate. Okay. Since the value of an asset at time t in the future is a random variable, so is the return I. Now you may consider the expected value and the variance of a return. Mu I is defined as epsilon, not epsilon, but expected value of Ri, and the variance, sigma I squared, is defined as the variance of Ri. It's called a risk. We also consider standard deviation. Okay, so that's pretty cool. Let's write these down. By the definition of weight, the sum of Wi is always 1. Okay, so returns. Returns is Ri is defined as VIT minus VI0 divided by the initial value VI0, or equivalently, this is the definition, VIT is VI0 times 1 plus the return. Okay, and mu I is defined as the expected value of Ri, and sigma I squared is defined as the variance of Ri, and sigma I squared is what we call the risk of AI. Okay, so that's the return. Let's continue. Portfolio return. Okay, so a return on the portfolio itself is defined as a weighted sum of each asset. Does that make sense? Does this make sense? Does it make sense to take the linear combination of returns? That's the question. Do Shrev stochastic? I can't. That's a copyright book, right? That's a copyright book, and I don't want a channel to get DMCA. Okay, so here you have the R as a linear combination, a weighted sum, a convex combination actually of Ri. Does this definition make sense? Because what I'm thinking is, why not? So here we're talking about the portfolio return. You know what? If you want me to do the Shrev book, one way I can do it is I put the book on the other screen or the physical book on my hand, and I'm just going to write everything on board like a traditional instructor. But then again, I wanted to facilitate question. Please make website tutoring. Please make website tutoring quant finance book like tutoring I'm willing to pay for it since your explanation is better than my goodness. Well, I know I'm leaving money on the table. I'm doing this for free on YouTube, but right now I don't have enough time to do that, and perhaps it's something that we'll do down the road. Okay, because I want to use the live stream I'm doing right now as basically practice, because as I said, I'm not a professional quant, so you guys are the guinea pigs. Okay, you guys are you're here to correct my mistakes, so this way I can produce something professional later. I think it makes sense, but because what I'm thinking is window. What I'm thinking is, why don't we look at the initial and final value together? Right? Let's assume theta is constant. Okay, let's assume theta does not change in the period. All the thetas are constant. So why don't we take the sum of I, theta I, VIT, and divide it by the sum of theta I, VI0. So that's the total. Actually, you need to minus that by 1. Okay, so why don't we take a look at this one? Does it make sense? So this is the total initial value divided by the total final value. Why not this one? This is a genuine question. It's not a bait, okay? It's not like something I already know and I just ask it rhetorically. This is why don't we use this? Because it doesn't seem to be the same as. Is this the same? Is this the same as this one? But the return is actually here. We're not even talking about expected return. This is just a random variable. Remember, I is a random variable. We're not taking expectation yet. Is this the same as what's given in the text? Well, you certainly got the WI thing going on. Let's write that down. So here you have WI, RI. Remember the definition of WI. The definition of WI is as follows. Here, WI is WI. Actually, here, WI naught. Yeah, I use WI naught. I use WI naught. Okay, so in the text, it used WI. So I put a naught here. I use WI naught because it makes sense to me, since the values are all initial values. Okay, so let's put that down. What's going on? Okay. All right, so here WI by definition is the theta I times VI naught over the sum of I theta I VI naught. Okay, this is WI naught times RI. What's the definition of RI? Use a different color. What's the definition of RI? RI is this one. Is VIT minus VI naught over VI naught. Okay, so this is RI. Okay, so these are just using definitions. And we can simplify. Looks like we can simplify. First of all, VI naught cancels. The denominator is sum of theta I VI naught over I. VI naught cancels and you get theta I VIT minus VI naught. Turns out to be the same. The quotient on the left side is flipped. Should be final value over initial. Yeah. Here, sorry about that. Final over initial. And I think what I'm trying to show is that the two definitions are equivalent. So this is intuitive. Okay, so here we have the simplification, and we get what? This is the on top, because here on the bottom, this is already a constant. Has nothing to do with I anymore. So you can simply sum over the numerator. The sum of numerator, sum of theta I, VIT, I minus the sum of theta I, VI naught. So it turns out to be the same. On the right is flipped actually, you want to get a percentage. This is also a percentage, but it's final over initial. This is how we typically calculate return, right? So the good thing is the textbook definition is equivalent to our own. As you can see, it's equivalent to our own. It's the sum over I theta I VIT minus sum over I theta I VI naught minus 1. So it's just straightforward algebra, the same as ours. So this is indeed correct. I mean, of course, this is correct. This is a definition, but it's the same as the definition I proposed earlier. So why not? This actually, they're not different. They're the same. Okay, so this is not a waste of time, because now we have two interpretations of the portfolio return. So the portfolio return has this intuitive definition: total final value over total initial value minus 1. So it's the total gain, okay, total change in the value over the total initial value, which is also the weighted sum of individual returns. So there are two ways to understand portfolio. So that's good. Okay, portfolio return is now understood. Now, here, for example, we have some concrete examples. Suppose the portfolio only has two assets with weights 0.4 and 0.6, and returns equals 10% and 8% respectively. And return of the portfolio is the weighted average, basically. 0.4 times 10% plus 0.6 times 8% gives you 8.8%. Right, so that's the portfolio return. Since the expected value operator is linear, the expected return of the portfolio as a whole is this one. So you just take expected value on both sides, right? As we mentioned, WI is considered constant. WI is not random, because WI is purely defined in terms of initial values. Okay, you don't change theta in mid-period, and the initial values are known. So nothing random here. And you just apply linearity. So here, even though this equation looks quite simple, we're using that assumption here. We're using the assumption that the initial values are constant, not constant, but rather non-random. And the theta are treated as constant as well. Okay, so the expected total return. So assuming theta I VI naught are constant, i.e. non-random, you have WI constant. And this applies, and you can give the mean return. Expected value of R equals the sum over I, WI expected value of RI. Or can write it as mu sum over I, WI mu I. Right, this is the expected return. There's no such thing as expected mean return, because that's redundant. Expected return of the portfolio. Okay, so I expect you would maximize mu given total variance, or you can do the other way. You fix you fix the total risk. You fix the total risk, and you want to maximize mu. Okay, so here, since the individual returns generally are not independent, you would use the the summation formula, right? We just derived that. So you have a linear combination of returns, a convex combination, in fact. Right? Convex combination means the coefficients, the weights, sum up to 1. Okay, so that's the total. This is a total return, right? This is a total. Yeah, this is the total. No, total risk. Total risk. So this is a quadratic function in Wi, whereas mu is a linear function Wi. Okay, so now we have the definition here. So we have the definition. Hang on, what's the name? Expected return and risk. Given a portfolio expected return is defined as mu sum of Wi mu I over I. Okay, and risk sigma square is sum over I, sum over j, Wi Wj, the covariance of Ri and Rj. And covariance of Ri and Rj is also written as rho ij sigma I sigma j. Definition of correlation coefficient. Okay, so these are two defining formulas, and we wish to write them in matrix form. Can we do that? The first one looks like a dot product, and indeed it is. It is a dot product. So you can write it as W vector transpose mu vector. The second is a quadratic form. As we mentioned, that's just W transpose times big sigma times W. Expected return and risk expressed in terms of matrix and vectors. And this should come in handy later on. Okay, let's continue. This is obvious. An asset is risky if its sigma I square is positive. It's risk-free if sigma I square is 0. So in that case, you have a degenerate variable. Until further notice, we'll assume that all the assets are risky. Okay, cool. More on risk. Let us take a closer look at the notion of risk. Generally speaking, there are two forms of risk associated with an asset. The systematic risk of an asset is the risk that is associated with the macroeconomic forces in the market. Okay, so you have, this is economic definition, okay, not mathematical definition, but still important because it will affect modeling choices, as I believe. Okay, you have systematic risk. Systematic risk is the risk associated with macroeconomic forces in the market as a whole, not with just a particular asset. Like Trump announcing there's going to be a new round of tariffs. That's a systematic risk, right? Or the Treasury adjusts the rate, right? So that's another systematic risk. And by the way, risk doesn't always just mean bad, okay? Risk isn't just bad. Right here, you see, risk is simply a positive variance. So sometimes risk can work in your favor. Okay, thank you very much, Windows Security. So yeah, risk doesn't just mean bad. Risk can be an opportunity too, right? It's just, in everyday language, risk seems like a bad word, but not in mathematical finance. It's just a fact of life that it simply means randomness. You can call it that way, fluctuations. For example,
A change in the market interest rate affects the market as a whole. A change in the nation's money supply is another example of a contributor to systematic risk. Global acts such as those of war or terrorism would be considered part of systematic risk. Fair enough. On the other hand, unsystematic risk or unique risk is a risk that is particular, okay, to an asset or a group of assets, for sure. Unique risk. Suppose that investor decided to invest in a company that makes pogs. There are many unsystematic risks here. For example, the customer may lose interest in pogs, or the pog company factory may burn down. All right? We understand that. A primer on how risks interact. Okay, so here we have a concrete example of how risks interact. The key difference between two types of risk is that unsystematic risk can be diversified away, whereas systematic risk cannot. Right? Unsystematic risk can be diversified away. So that's cool. That's good news. Whereas systematic risk cannot. So let's put that down in our notes. Risks. So you have systematic, which are macroscopic, macroeconomic. For example, interest rate change. Cannot be mitigated. Right? So another one is unsystematic or specific. Okay, so these are special. The risk due to things are just existing. Yeah. Unique to specific assets. For example, my YouTube channel being hacked. That's an important system, a specific risk, right? And it can be mitigated through diversification. For example, I have Math with Ming 2.0, so go ahead and subscribe to that channel as well. All right. So these are modeling issues, which are important. We're not just splitting hairs here. All right, let's keep going. Here you have a specific example of how the various risks interact, right? So an investor can, for instance, an investor can reduce or eliminate the risk that a POG company's factory will burn down by investing in all POG making companies. Okay, so this way, if one POG factory burns down, another POG factory will take up the slack. More generally, an investor can reduce the risk associated with an apathy for POGs by investing in all toys and game companies. Right? So if, let's say, the consumers lose interest in POGs, they might pick up something else. Right? Deposit in a bank. If one changes the bank, but the whole bank system could collapse, and we're screwed irrespective of the bank one truth. Yeah, that's certainly true. Okay, hopefully that won't happen. God forbid. Okay. If this way, if the POG factory burns down, okay, we already read that. After all, when was the last time you heard a child say he's tired of buying POGs and decided to put his allowance in the bank instead? That's funny. And, well, that can happen. So, to see the effect of individual assets upon risk, consider a portfolio. Okay, so we have now a concrete problem. So, you now have a portfolio with single asset A1, with expected return mu1 and risk sigma 1. The overall risk of the portfolio is, of course, sigma 1 squared. Right, so that's just one asset. Now you add one additional asset, and suppose it has expected return mu2 and a risk sigma squared 2. All right? So now you just have a single variable optimization problem. What's that? Well, you just need to decide the weight of asset A1. Let's call that T. Then immediately the other asset A2 has a weight of 1 minus T. Right. So as mentioned, the expected return is just the weighted average. T times mu1 plus 1 minus T times mu2. So that's the total return, right? Expected total return of the portfolio. And then you have the risk, which is a quadratic function. Right. So the quadratic function, it looks a little bit messier, but really is just this formula here. Okay. The weight T squared times the standalone risk of A1, just sigma 1 squared, and the weight 1 minus T quantity squared times the standalone risk of asset 2, and then you have the interaction term, right, the covariance term. So what do? How does this risk compare to the risk of individual assets in the portfolio? We may assume that asset 1, sigma 1, is at a lower risk compared to asset 2. So sigma 1 is less than or equal to sigma 2. You can always do that. If not, you can just reverse the order. All right. So now you have these two functions. And what do we do with them? I guess you will set one to be fixed and minimize or maximize the other. Right? That seems like an intuitive idea. You want to fix the expected return and minimize the risk. Or you want to fix the risk and maximize the return. Both are okay, I think. Okay? So now you have certain possibilities. So basically, purely look at the function sigma squared. Purely look at the function sigma squared. Because t has a range. T is in 0 and 1. T is in 0 and 1. So the quadratic function might behave a little bit differently in that range. So you got these situations. So first of all, a quadratic function here, the quadratic function is obviously convex, meaning, like this, like a smile. The quadratic function is obviously convex, is unbounded above. And the critical number where the derivative vanish, or the axis of symmetry, you may call it, may or may not be in the range 0 to 1. Right? Like this, here. If you take the derivative and set that to 0, which we can easily do in a second, the global minimum point, Tm, may or may not be in 0 to 1. Right? Here you have, on the left, you have Tm within 0 to 1. On the right, you have Tm outside of 0 to 1. In which case, sigma squared is a monotone function. As you can see, if we wish to minimize sigma squared, you just set t equals 1. So everything is in asset 1 now. So that's the second scenario. And the third scenario is perhaps highly interesting. Qualitatively, it's the same as the first one. You got TM in the middle between 0 and 1. But here you have this interesting choice that by balancing the portfolio appropriately, you can achieve zero risk. So here you have a zero risk scenario. So it is possible to let sigma squared be 0. Sean, if you could recommend one book for mathematical finance with these levels or required prerequisites without worrying about the copyright for the stream, what would it be? Or does this one? It would be Shrev. Yeah, it would be Shrev. Well, I guess there are different purposes. So let me just put out a list of recommendation. So, mathematical finance uses various levels of mathematics, of course. Even without a background in calculus, you can start with the financial mathematics. Hang on, let me just put down a basic book which I find very interesting. Not interesting, but very standard. It's not so interesting, but it's kind of boring actually, but it gives you the necessary foundation, something that you would probably need. Financial mathematics, theory and practice by Brown and Kopp. So this one, which I just sent, this is no calculus needed, okay? Just no calculus needed. So this is really a good way to get started with the basic ideas of financial mathematics. This is more, I should say, more similar to, it has a lot of overlap with actuarial science. So this is very good for the beginner. It has no probability, no stochastic, but still it's important, right? Because these fancy mathematics, okay, which we were doing right now, are augmentation of those basic stuff. And now as the second one would be, you would probably move on with Shrev. Shrev Volume 1 and 2 are the standard, the gold standard. Okay, Shrev Stochastic Calculator Finance, Volume 1 and 2. Volume 1 and Volume 2 can be read independently. Okay, Volume 1 is discrete models only. You can go straight into Volume 2. And do know some calculus, linear algebra, multivariable probability applied for machine learning. Yeah. This book, I think, is the right level for you. This book I'm doing right now is probably perhaps the best first introduction to you. First of all, it's free and it covers all the basics. But just be a little bit more careful because I do spot some mistake. You know what? Let me a good one actually. I think it's in the bibliography. Another nice thing about this book is that it has a solution manual. Okay, so do we have Ross? Yes, Ross. How can I forget Ross? Anything written by Ross is great. Okay, so hang on. Anything written by Ross. Oh. Okay, I cannot copy for some reason. So basically Ross, let me put it down in chat. Ross, an introduction to mathematical finance. Okay. Options and other topics. Pretty sure this is not measure theoretic. So Shrev Volume 2 uses measure theory, but it's rather gentle. Okay, I would consider Shrev to be overall intermediate level when it comes to stochastic calculus. And second book, an elementary introduction to mathematical finance. Yeah, that's also good. Probably a good level for your level. My math knowledge is all over the place. Law just yesterday to brush up statistical physics with management. That's very advanced. That's very advanced. So you're talking about non-equilibrium statistics, non-equilibrium statistical mechanics, management equations and all. That's stochastic calculus. That's already very advanced. No, not that they're bad for that, but worth noting. Yeah. So yeah, that's a book recommendation. I'm pretty sure there's a lot of good books out there, but these are just the ones I'm aware of and have some experience with. But I do not claim to be an expert because I'm not a professional quant. Okay. Here, let's continue. So we define two main quantities. One is the expected return and the total risk. Right? And now we have this toy example of just two assets, and we already can see there's some interesting cases going on. Okay. Here, suppose you have uncorrelated assets. Then the cross term vanishes. You know, it is intuitive that because both assets are risky, right? They're both risky and they're uncorrelated. So it is impossible to balance them to get a perfectly riskless asset. So it's a perfectly riskless portfolio. So that's quite intuitive, right? So that's exactly the first diagram. If you have rho equals zero, then a minimum will always exist somewhere in the middle. Okay, so the minimum will always exist. A bit of a differentiation shows that. Okay, so because right now we're a little bit short on time, so I'll just hand wave through this. Okay, I assume everybody can do differentiation. Okay, by setting the second term to 0, you can differentiate the quadratic function. I'm not going to do that algebra. Okay, set that to 0, you get Tm in the middle, so that's the minimum risk combination. You get the minimum risk combination and you get the minimum risk value. Okay, and it is clear that, it is clear that the minimum risk lies somewhere between. What? The minimum risk should be lower than both. Look at the diagram here. This is sigma 2 square. This is sigma 1 square. It should be lower than both. Okay. I can't hand wave because I now have to do the algebra. So, okay, two asset model. Okay, two asset model. Let's do the two asset model. So you have given mu1 sigma 1 squared, mu2 sigma 2 squared. Okay, and mu as a function of t is t mu1 plus 1 minus t mu2. Okay, and sigma square of t is t squared sigma 1 squared plus 1 minus t squared. It's 2 t 1 minus t rho 1 2 sigma 1 sigma 2. Okay, case rho 1 2 equals 0. This way sigma squared becomes t squared sigma 1 squared plus 1 minus t. Oh, by the way, t is between 0 and 1. We have the two formulas. Okay, so d sigma square over dt. Do the differentiation, 2t sigma 1 squared minus 2 times 1 minus t quantity Okay, chain rule, and sigma 2 squared. Set this to be 0. You get t sigma 1 squared equals 1 minus t sigma 2 squared. T sigma 1 squared equals sigma 2 squared minus t sigma 2 squared. All right, so t is sigma 2 squared over sigma 1 squared plus sigma 2 squared. Cool. So this is always between 0 and 1, so we're good. Okay, so let's call this Tm. Okay, so what's sigma squared at Tm? Do the algebra real quick. T squared is sigma 2 to the 4th over sigma 1 squared plus sigma 2 squared quantity squared times sigma 1 squared. Okay, and 1 minus t squared, which is simply sigma 1 squared over sigma 1 squared plus sigma 2 squared, quantity squared, sigma 2 squared. Okay, simplify. You get sigma 1 squared plus sigma 2 squared, quantity squared at the bottom. And on top, you get, hang on a second, sigma 2 to the 4 sigma 1 to the sigma 1 squared plus sigma 1 to the 4 sigma 2 squared. It's different, huh? It's not the same as what we've seen in the text. What the hell? This quadratic in t, this quadratic in t is shown on the left, right? This is a diagram. A bit of a differentiation to show that this is correct. This is what we got. See? Our Tm is sigma 2 squared over sigma 1 squared. Yeah, this is what we got. Am I stupid? This is t. T is this. So, what the hell? Or is there something that can be simplified? Which I mean, oh, okay. Actually, I think I forgot to do the simplification. So you can take out sigma squared, sigma 2 squared, sigma 1 squared, and then sigma squared plus sigma 1 squared. Okay, so now it works out. Is there a 2 somewhere? How come there's a 2? Look at that. Why on earth there's a 2 here? Bro, that's not right. Because, this is less than both of sigma 1 and sigma 2, which is what it's supposed to be. Okay, when t equals 0, you get sigma 2 squared. When t equals 1, you get 1 sigma 1 squared. Actually, sigma 1 squared, sigma 1 is smaller, huh? Yeah, sigma 1 is smaller. Let's assume that. Hang on. Oh no. Okay. Here. Assume sigma 1 is less than or equal to sigma 2. Isn't the 2 not... I don't think there should be a 2. Here, this is the algebra. Just plug in, there shouldn't be a 2. This is TM. Right? Intuitively, it should be less than both. Okay, so this is, I think that's another mistake in the text, no? Which is annoying. I think in the book, except the one you show, there wasn't a 2 in the TM. TM has no 2. See, this is TM, and this is the TM that we got. It's the same. Sigma m squared is supposed to be the minimum risk, which is sigma squared evaluated at TM. There's no 2. Very odd. So in fact, we can conclude that 1 over sigma squared equals 1 over sigma 1 squared plus 1 over sigma 2 squared. So you have this relation. And of course, this is less than or equal to 1 over, well, actually, this is greater. Of course, this is greater or equal to, and this is not a typo. So sigma m squared is less than or equal to sigma I squared. I equals 1, 2. The overall risk, the portfolio risk is no greater. Is no greater. Actually, it should be strictly less. Strictly less than. It should be strictly less than individual risk. But here in the text it says the minimum risk somewhere lies between. With a 2, then it's true. Right? With a 2, then you get what is so-called a harmonic average. You see, this sentence here contradicts the picture. My goodness. Hold on a second. It's like this book is actually well cited. That's why I use it. My God. Stephen Roman. Math Finance. Guys, take a look. This is cited by this is the book Introduction to Mathematical Finance is cited by 147 people. This is a Wikipedia page. Actually, this is not the same. Oh, this is a different person. It's a different person. He wrote the Advanced Linear Algebra. This is not the same person. But yeah, this is a well-cited book, but somehow I don't get it. This is not a typographical. It's not just the fact that there's a 2 extra 2. The interpretation is also wrong. Because this sentence, the minimum risk lies somewhere in between the risk of individual asset, follows from this formula. As we showed, the overall risk is strictly less than individual risk. It's not in between. It's such a simple problem, right? It's a high school algebra problem. but somehow this is messed up. Oh dear. Or am I being extremely stupid? Because look at the picture. The minimum sigma square is less than both. Yeah, it cannot be in between. So if you just wanted, if the result is in between, you just pick, well, you just pick sigma 1. You just put everything in 1. Right? This is not good. Damn, bro. Okay. Let's get on with it. Let's get on with it. Suppose that the assets are perfectly positively correlated. And suppose you have perfectly positively correlated, then in that case, you have a you have a complete square basically. You have a complete square, and to minimize sigma is to minimize what's inside the bracket. T sigma 1 plus T minus 1 minus T sigma 2. Okay? Okay, and here, because this is just a linear function with T in 1, 0, and 1, right? This critical point, Tm, cannot actually be achieved. Yes, the interpretation is based on the wrong math of 2. This is wrong. So, we don't know. Okay. By the way, what's the current edition of the book? Maybe they fixed it in the newest edition, huh? The second edition. This is second edition. This is 2012. What book is it? It's in the link. Link is in the description. This is 2003. Yeah, I mean, you can still read it. There's no problem. Still, but I guess this is perhaps an older edition that some of the mistakes aren't fixed. Yeah, this is very much, I guess, the draft of the text. That's why it's freely available. Yeah, thank you very much for recommending books. This is very helpful for me to prepare stuff. But as far as live stream is concerned, right now I can only do resources that are open source. Will the stream be uploaded? Of course. Once the stream finished, the recording is automatically uploaded to YouTube. Just go to the stream tab of my channel. Yeah, just go to live tab of the channel and you will see all the live streams. Okay. Well, 27 people watching. That's crazy. Pretty good. Pretty good. It's better to read books of practitioners. I know, of course, we want to, this is the goal, but, there are certain restrictions I can do on stream. Right? Is there a difference with the current theory? Well, this is fundamental stuff, right? Of course, this is still, as an introduction to math finance, this is what we are doing. This is very simplistic. It's very simplistic. There's nothing wrong with the math except for, the mistake that we just spotted. These are fundamentals. These are Nobel Prize winning models, right? Even though you don't use Black-Scholes, for example, literally every day, this still provides important intuitions for you to expand upon, right? So yeah, let's in physics, you assume there's a spherical cow. Right here, we're doing basically spherical cow, but still spherical cow tips inside. So, yeah, that's why it's simpler model like CAP-M and Black-Scholes are still worth studying as illustrations of the fundamental principles. Okay. Anyway, so here, and because fundamental principles are sometimes glossed over, unfortunately, and this will create problems down the road. So that's why we're very careful, try to be as careful as we can about definitions and verify the details. Okay, so here we have the second scenario where Tm is strictly greater than 1. Right? Tm is strictly greater than 1, so this is actually not achievable. The minimum risk, actually the minimum risk should take a short position. Oh, you can take a short position. You can take a short position. Yeah, sorry, my mistake. I guess it will need to do with software because a lot of math is in software. Yeah, the software stuff is a tool. Software is a tool. Eventually, when you do real-time calculation, then of course you need to use software, right? But as a first introduction, everything must be done in pen and pencil, in my opinion. I mean, pencil and paper, in my opinion. This way, you understand what is actually going on under the hood. Right? I mean, this is math with Ming, not computer science with Ming, right? So that's why we're doing things the old-fashioned way. Here I made a mistake earlier because I forgot you can do short position. Okay, it is possible to have negative assets. It is possible. Okay, so yeah, of course, computational methods, right? Software relies on computational methods. Computational methods for mathematical finance is once again a hugely important subject on its own. Right? It involves things like numerical PDEs and numerical optimizations, and also a Monte Carlo simulation. So this is a very diverse and interdisciplinary field. Right? But still, the fundamentals are here. Like here in this chapter, the main theme is optimization. The 2012 book doesn't have this portion. Okay, what's going on? Okay, anyway, I'm glad that it is covered, right? Because still, CAPM is very important. Perhaps they deleted for some reason because most of the book is kind of the book is imbalanced in terms of its allocation, right? So most of the stuff are in asset pricing, option pricing. So CAPM is more like a standalone subject. But I chose this topic because it's accessible. You just need basic probability. You don't need stochastic process and just some linear algebra and calculus. You can study this topic. And it won the Nobel Prize. So it's pretty valuable on its own. Okay, and finally you have a perfectly negatively allocated, perfectly negatively correlated assets. So in that case, well, you have perfectly negatively correlated. Remember what that means, though. Remember what that means. The return, this means the return of asset 1 and asset 2 satisfy the linear function. So let's think about the middle situation. Rho 1, 2 equals 1. So if rho 1, 2 equals 1, so that means asset 1 and asset 2 are perfectly correlated and the correlation is positive. That is to say, if asset 1 return increases, the asset 2 also has the return of asset 2 also increases. Sorry, I'm getting a little bit tired there. So, well, here we assume that asset 1 has a lower risk. So it makes sense that because asset 2 and asset 1 have a perfectly positively correlated return, to minimize risk, you just put everything in asset 1. Right. So that gives you the lowest risk, and the risk is just sigma 1. Here, once again, we're considering risk only. We're not considering returns at all. Okay? We're not considering mean returns at all. The goal is simply to minimize risk. Okay? And for the opposite scenario, where you have perfectly negative correlation, the third case, so it's possible to choose an allocation so that the risk is eliminated completely. Right. So in the third situation, sigma t is also a quadratic function that is a complete square. Right. So to minimize that, you just set the base of the quadratic to be 0, and the Tm turns out to be positive. So both assets are in long position. Does not require short selling. The minimum risk portfolio does not require short selling. So as a summary, thus the case where the assets are perfectly negative correlated seems to be the most promising. It seems to be the most promising in that the risk can be reduced to 0 without short selling, which certainly has its drawbacks. Indeed, short selling may not even be possible in many cases. When it is, there can be additional costs involved. Of course, it is in general a difficult or impossible task to select assets that are perfectly negatively correlated with other assets in the portfolio. Right, so that's the main takeaway here is when you have perfectly negative correlation, you can achieve 0 risk without short selling. Okay. Here I'm just gonna skip the math now. I really want to get to the matrix, or yeah. Why don't we get to the? Can we get to the matrix part? Can we get to the matrix part? Not quite. Not quite, huh? Yeah, this is the matrix part. Actually, you know what? Let's look at the matrix part. We'll give the definition of matrix part, and then we'll come back, okay, to the two assets once again. Let's take a look at the matrix formulation. Here, multi-asset portfolio. Now let's turn our attention to portfolio with arbitrary number n greater or equal to assets, n greater or equal to 2 assets. The weights of the portfolio can be written in matrix form. Okay. Once again, we're not assuming that W's are positive. I've been making that mistake quite consistently for the last 30 minutes or so. So my apologies for that. Here, W does not have to be all or non-negatives. Okay. So they can be negative, but they still need to satisfy the condition that they sum up to 1. So that they sum up to 1. So that's the condition here. So in terms of geometry, the vector W lives in a hyperplane. It's not in a subspace. This is not a subspace because it does not pass through 0. So geometrically speaking, this is in a subspace. Okay? And we can write this as a matrix product. So O matrix, or a column, actually this is a row vector. Yeah, a row vector of 1. A row vector of 1, O times W transpose equals 1. So that's the matrix form. The constraint on W. Okay, this is a constraint on W. And M, the mean return vector. Mean return vector, I suppose this is treated as a constant. I suppose all the assets mean return, and then the risk or no. Okay, so this is once again matrix notation. M is a row vector, consists of mean returns. And the covariance matrix, Cij, we defined that earlier. Cij, the entries are just covariance between Ri and Rj. C is symmetric, positive, semi-definite, or simply positive. Okay, simply positive. Here we shall also assume C is invertible. Okay, we assume that C is invertible, which in this case implies that C is positive definite. Why is that? Why is that? That's a linear algebra fact. That's linear algebra. So if you already have a symmetric positive semi-definite matrix, and you know that it is invertible, it must mean it is positive definite. It must mean it is positive definite. How do you show that? Well, perhaps the easiest argument is to use eigenvalues. Okay, if C is invertible, it means, so first of all, C is symmetric. First of all, C is symmetric, then it means all of its eigenvalues are real. These are all real. Okay, and because C is positive semi-definite, all the eigenvalues are non-negative. Okay, and now we're making an extra assumption that C is invertible. Invertible means invertible on its own means no zero eigenvalue. All eigenvalues must be non-zero. But we already know that all the eigenvalues are non-negative. This must mean that all the eigenvalues are strictly positive, and therefore C is positive definite. So that's the argument. Okay, so C, the covariance matrix here, is assumed to be strictly positive definite. No, strictly positive definite. This means it is impossible to get a zero risk portfolio. Okay? It is impossible to get a zero risk portfolio unless you, well, assign every weight to be zero, in which case there's no portfolio at all. Okay, so that's the assumption here. Okay, so there's always risk. Right? Remember, we made that assumption earlier. So this C being positive definite just reinforces that assumption. Okay, so the expected return is a matrix product. Then the risk is a quadratic form. And actually, this bugs the heck out of me. this bugs the heck out of me because in mathematics we write W transpose M, right? We do that there. Or mu M transpose, we'll put the transpose before, not after. Because we're used to vectors being column vectors. But I guess this is fine. We can live with that. This is okay. Actually, you know what? In probability, actually I think in stochastic process, like in Markov chains and whatnot, we tend to use row vectors. So I guess it makes sense here. Here's W is a row vector and it's sum up to 1. So it kind of like a probability vector. It kind of like a probability vector, so we use it as a row vector. Even though it's not. I mean, it's not a probability vector because things can be negative here. Okay, so we're using W as a row vector. You know what? Let's change the notation because we don't want to confuse ourselves later on. Even though this is a standard linear algebra notation, let's follow the convention here. M times W transpose, okay, little t, and W transpose. Let's conform to the textbook notation. Okay, so the vectors are all row vectors. Okay, so these are all row vectors. The Markovich bullet. Markovich, you guys know this name? Markovich. Markovich, I believe, won the Nobel Prize in Economics in the 50s. Markovich portfolio theory, or modern portfolio theory. Markovich, Harry Markovich. Oh, he won the prize as late as 1990? But it came out in the 1950s, right? Yeah, it's in the 52. Wow. Right? So Harry Markovich, that's the guy. Speaking of which, using O not for the zero matrix is also weird. Exactly. Exactly. I don't know. I typically use a bold 1. I use a bold 1 for the 1 vector. It's okay. We can live with that. So why did he use that a row vector? Why didn't he just call it like we used to? John Barnes, good question. I was just on that point. Why do we use row vectors? Because, I mean, this is my suspicion or my speculation. Because in the theory of Markov chains, we use row vectors as probability. For example, in the theory of Markov chain, we denote a row vector as a discrete probability distribution. So imagine W is our probability. And there we typically use row vectors. So here, because W satisfies this quote-unquote normalization condition, it looks like a probability vector, even though it isn't. Right? Because here W's can be negative. You allow short position. I guess it's just for that reason. Okay? Yeah. In linear algebra, we typically assume a vector is a row is a column vector, unless otherwise specified. Because in linear algebra, the row vectors are really covectors. They are matrix representations of linear functionals. They live in a dual space. So the choices in linear algebra are not arbitrary. The row vectors lives in a dual space. But here, I don't think there's any particularly deep reason that we're using row vectors. It's just something that we get used to, okay? Which is not a big deal. All right, so let's examine the relationship between the weights of a portfolio and the corresponding risk expected return point. Actually, you know what? I think we need to go back a little bit. All right, so the risk expected return point is something that probably is in the earlier part of the book. Okay, so we want to examine the relationship between the weights, the W vector, and the corresponding point, sigma mu, given by the equations above. So mu and sigma. What does that mean? It means when you vary W, remember, mu and sigma are functions of W only. Okay, so here big M and big C are given, are given. So you can think of mu and sigma squared together form a parametric curve, with W being the parameter. Of course, this is not the typical parametric curve you've seen in regular calculus where you just have one parameter. Here you have multiple values. Right? But the point is, given a W, mu and sigma is determined. Then you can plot that as a point. So sigma and mu together form a combination. On the plane sigma mu. On the half plane, actually, it's because sigma is positive. The point is, given W, you can determine sigma and mu. And you're just going to trace out. You're going to trace out all of those combinations. Right? So right now you're not doing optimization at all. Right? You're just considering all the possible values. All the possible values of the pair sigma and mu. So if we go back a little bit, because that's probably easier to visualize, here. So remember, in the two asset scenario, we just need to tune one parameter, right? In a two asset scenario, here we have the formula with us. In a two asset scenario, we just have one parameter t, just the weight. What you can do is you can eliminate t in these equations. You can You can, for example, solve for t from the first equation and substitute t in terms of mu into the second. And of course, sigma being a quadratic function of t is a quadratic function of mu, and therefore you get this parabola shape. And you get this parabola shape. So this is actually, that is something that holds in general. Of course, this needs to be shown. But basically, even when your variable for mu and sigma is now a vector w, the graphic stays the same. The graphic stays the same. So remember, as we mentioned, w lives in the hyperplane because they sum up to 1. And as you vary the point on the hyperplane, on the hyperplane, it no longer traces out a curve, but rather a region. If that makes sense. Okay, because right now, if you have more than one, so to say, if you have more than 1 degrees of freedom, because in the two assets problem, you just have 1 degrees of freedom. Sorry, here in the two asset problem, you only have 1 degree of freedom t. So the relation between mu and sigma squared is a curve. But imagine now you have more than 1 degrees of freedom. So you have 3 assets, so to say. In 3 assets, you cannot solve for the weights exactly, simply given mu. Here in the 2 asset case, you can. Given mu, you have t. There's a 1-to-1 correspondence between the two. So therefore, sigma squared is a curve. Sigma squared and sigma and mu is a curve. Okay, sigma mu is a curve. Actually, sigma squared is a quadratic function. Sigma squared is a quadratic function, whereas sigma and mu is a hyperbola, I believe. Is a hyperbola. So now, if you have more than 1 degrees of freedom, here for example, you have 2 degrees of freedom. You have 2 degrees of freedom because there is a constraint between w. Okay? And in that case, possible combinations of mu and sigma is a region. It's not just a boundary anymore. But the boundary is still important. It's called the Markovich efficient frontier. And what do we mean by efficiency will be discussed later. And this region is called, it looks like a bullet. It looks at the tip of the bullet. So it's called the Markovich bullet. Okay, so let's read the whole text. Right, so let us examine the relationship between the weights W and the corresponding risk expected return point, sigma mu, for that portfolio, given by the equations above. Note that we're now referring to risk in the form of the standard deviation, sigma, not in the sigma square anymore, okay? Just the sigma. Figure 5 describes the situation in some detail for the portfolio with 3 assets, and this will provide some geometric intuition for the multi-asset case in general. We'll define the terms Markovich bullet and Markovich efficient frontier a bit later. So here's the intuition here. The left-hand portion of figure 5 shows the n-dimensional space in which the weight vectors reside. Okay? So that's just a hyperplane. Okay? It's not a subspace, but a hyperplane. The hyperplane is, of course, W1 all the way to sum up all the way to Wn is 1. Now, if n equals 3, it's the ordinary 3 space, the plane in the 3 space, passing through these points. For the sake of clarity, the figure shows only that portion of the plane that lies in the positive orthant. Okay? So it's only in the region where the 3 W's are all positive. But of course, this can be extended, as indicated. Okay? So here you have the constraint. And as W varies on that plane, sigma and mu as a combination fills this region called the Markovich bullet. Now let's see what the text has to say. We denote by f the function that takes each weight vector in the weight hyperplane to the risk expected return. Risk expected return. So this is risk is sigma, expected return is mu. So sigma mu ordered pair for the corresponding portfolio. So now you have a function that takes n inputs. Okay, and more specifically, actually, you should take n minus 1 inputs because there's only n minus 1 degrees of freedom. And returns 2 outputs. Returns 2 outputs. Okay, so that's the function. Okay. Mu and sigma square is defined earlier. The function f is also pictured in figure 5. Right, so that's the function f. So you can understand that as an abstract mapping because it's not easy to draw the graph of f, unlike in the two-asset case. Right, so it's not easy to draw the graph of f, but still, a point on the hyperplane is now mapped to a point on the sigma mu plane, and we're interested in the range. We're interested in the image of that function. Okay, so now we have this situation. The f is also pictured in figure 5. Our goal is to determine the image of the straight line. Image of a straight line in the weighted plane. Image of a straight line in the weighted plane under function f. This will help us to get an idea of how the function behaves in general. It is analogous to making a contour map of the function. Okay, so how do we do that? How do we do that? Okay, so there's some appears to be some linear algebra going on. Okay, so let's do this part of the derivation, and then we will finish the stream. How about that? Okay, so I guess is everyone clear about the geometric intuition? It maps weight vectors into the sigma mu plane, and we're interested in the image. What sort of subset of sigma mu plane it turns out to be? Right, that's the it turns out to be the Markovich bullets, of course. But let's take a look at the derivation here. Okay. So it seems like everyone is on board, so let's keep going. If you have questions or spotted mistakes on my part, be sure to call it out in the comment, in chat. So here we have the equation of a line in the n-dimensional space. The equation of a line in n-dimensional space, whether in the weighted hyperplane or not. Okay, this makes sense. This makes sense because each component. So here, for some reason, we're still using the row vector, so that's fine. Let's just get on with it. So here, each component is a linear function in T. A1, B1, all the way to AN, BN are all constants. Okay. So there's no constraint whatsoever. So this is not constrained to the weight plane. Let's go. The value t equals 0. My cats are knocking things over from the table. Typical cat, but what else can it do? The parameter t varies from minus infinity to infinity. The value t equals 0 corresponds to the point a1 all the way to an, and t equals 1. Hang on, hold on a second. What? T equals 1 corresponds not b1, right? It should be a1 plus b1 all the way to an plus bn. Okay, another silly algebra mistake. We're used to that. Okay. T1 corresponds to a1 plus b1 all the way to an plus bn. Okay, this is obviously a silly mistake. But we'll follow the overall argument. So that's why it's important to write your own notes. Sometimes you see mistakes and you can immediately correct them. It is also true that any equation of this form is the equation of a line. Sure. Now for any point W on the line. So W is a point on the line, huh? we're still in the W space, but we aren't considering the plane anymore, just an arbitrary line. See, this is an arbitrary line. This is an arbitrary line, and what do? We plug the point W1 all the way to Wn into the expected return function. So of course, mu is mu1 W1 plus all the way to mu n Wn. W1 all the way to Wn is on the line, so W1 equals A1t plus B1, and Wn equals ANT plus Bn. And then you just substitute and simplify. Substitute and simplify, you get this form, mu1 A1 plus all the way to mu n ANT plus mu1 B1 plus mu n Bn plus mu n Bn. So nothing super complicated here. So this tells you, okay, so this tells you as t varies. T varies means the point on the point on the line varies. The point in the W space varies. As it goes on, mu also, because it's a linear function, mu is a linear function of W, also traces out a line, which is a linear function of t. This is a critical point. I guess this is important critical point in the sense of important information, not derivative equals 0. Okay, this draft feels like a draft version of which from this so many errors. Yeah, unfortunate. That's unfortunate. Okay, but still, I mean, let's. I tend to be. That's just personal opinion. I tend to be rather lenient when it comes to draft because I know how much effort you need to put into writing such things, and it's, I guess, like for me, I have this attitude that something is better than nothing. Okay, it provides us with a material to engage with rather than information to be received. Okay, if you're on this channel for a while, you know I always have this attitude of auditing. Okay, something, it doesn't matter who write it. Okay, it could be Terence Tao or Leonard Euler himself. Okay? If it's a math, if it's something in math and I read it, I always take the attitude of active auditing, even though sometimes I might not be always. I mean, of course, I wouldn't be able to understand everything. I will just admit I don't understand. Okay, I don't understand, and therefore I cannot determine whether this is correct or wrong. But for the sake of keep reading the document, I can assume that to be true. But whenever I spot something that doesn't make sense, I will not just gloss over it. So that's the mentality here. So, but basically, this is an easy mistake to spot. Some of them are not so easy to spot, right? Especially for beginners, like the independence thing. Pairwise independence does not imply full independence. So that's something that is quite subtle, and I don't think that's fair for a beginner to spot. But even for beginners, this sort of mistakes can be easily spotted, right? And here, the previous one, this is something I think is also quite important, right? The first case, which we verified, right? This is an important, somewhat of an important mistake in my opinion, because the conclusion is wrong, right? Okay, I'm sorry, but if you guys have a better option, like open source book that I can stream, then please let me know. Okay, I'll be more than happy to take a look at in the future streams. Okay, we're doing what we can here. All right, so here we have, let's continue. So mu is a linear function of t. Why is that important? Why is that important? Well, so you can solve for t. You can solve for t. Let's write t as a function of mu, which is also a linear function mu. Right? Here we use the symbols a and b for convenience. Right? These are just two big constants. And I must assume that the denominator above is not 0. Right, let's assume that this is not 0. So basically, this assumes the direction vector A. Now, A1 all the way to AN is a direction vector. The direction vector of the line is not orthogonal to the mean return vector. So that's what we're assuming. Okay, so now let's take a look at the risk. Well, you have the risk function, which is a quadratic form of W, and you plug in the components Wi, Wj, and you expand. These are all just mechanical calculations, and you just get a quadratic function in T. Okay? Sigma squared is a quadratic function in T. So now we can substitute T as a function of mu into sigma squared. So these are all straightforward algebra. And then we substitute T equals A mu plus B into the expression for sigma squared. This way you get a quadratic. So this, what's that? Well, this is a quadratic in mu. Sigma squared is a quadratic in mu. Sigma squared is a quadratic in mu, and I believe you can determine its geometric form. Its geometric form. So sigma squared is a parabola of mu. So the risk expected return point sigma squared. Notice this is sigma squared. Sigma squared is a quadratic function in mu. So the point is, as t traces out a line in the weight hyperplane here, as t traces out a line in the weight hyperplane, like so, on the sigma square mu plane, you have a hyperbola. This is a little bit different from this diagram because we're dealing with sigma, not sigma squared. Sigma and mu. This is sigma and mu. But if you're dealing with sigma squared and mu, you should get a parabola lying on its side. On its side, because sigma here, sigma squared, that's the risk, is a horizontal coordinate. The horizontal coordinate is a quadratic function of vertical coordinate, therefore the parabola lying on its side. Hold on a second. This is another typo. Not in the sigma mu plane, but in the sigma square mu plane. If the coordinates is sigma, then you need to take the square root. That becomes a hyperbola. Okay, so this is another mistake. This is sigma square mu. Okay, not sigma mu. Taking the square root in the first corner produces what we call a Markovitch curve. This term is not standard, okay? So this is the Markovitch curve simply refers to the image of a line, right? The image of the line of this function. Actually, it should be a square. Already taking the square root. So yeah, a Markovitch curve in this book refers to the image of a line in the W plane under this function f. So why is that? This is not standard. That's the straight line in the weight hyperplane. The straight lines in the weight hyperplane are mapped to the Markovitch curve in the sigma mu plane under the function f. Note that the Markovitch curves are not parabolas. Yes, exactly. Sigma squared is a parabola. Sigma mu is not a parabola. Sigma mu is actually a hyperbola, should be. It should be a hyperbola. And now we have some actual numbers. Here we have some actual numbers. So, hang on. Shows an example of Markovitch curve generated using Excel. For further reference, we know that the data used to generate this plot this curve. Hold on a second. You can't just use these numbers and get a curve. Remember, to get a Markovitch curve, you need to select a line. the image of a line is the Markovitch curve. So yeah, you have these parameters. You have these parameters, but if you don't know the line, we don't know what this curve. We don't know we don't know how to reproduce this. But as we can see, this is not a parabola. You see, it's remarkably flat at the near the end, basically. This is in fact a hyperbola. It's in fact a hyperbola, but there's still missing information here. We don't know which line is it talking about. We don't know which line is it talking about. So something is missing here. Okay, so right now we're approaching the end of the stream. I apologize, everyone, because I didn't have experience with this book before. Okay, I just want to briefly remark that it still remains to be proved. It still remains to be proved that the Markovitch bullet looks like this, or should we say, it still remains to be proved that the image of f is the Markovitch bullet, which is a purely mathematical problem. Okay, so you have this function w. We wish to show that the image of the hyperplane under w is the Markovitch bullet. Okay, and that's it for today's live stream. Okay, I hope what we did was useful for those to tune into the stream. Okay, we may or may not continue this in future, but if you have feedback, please let me know. And I don't think this is a terrible book. Okay, I don't think that for all its flaws, I don't think it's a terrible book, because it's quite gentle. It's quite gentle, and it covers the fundamentals. Even though there are mistakes I'm not saying everywhere, but if I write my own notes, okay, I'm pretty sure there's going to be more mistakes than this one. So I'm pretty lenient when it comes to that. Okay, the important thing is there is some material we can engage with and we can learn. So that's it for today's live stream. Okay, and if you have further questions, thank you very much. I like the general outline of this, despite the mistake. Yeah, I like it. Right? I like it. It could be, you know what? Vernon mentioned in the new version that CAPM is simply deleted. Oh, it's just arbitrage, option and arbitrage now. Okay. Oh, actually, he wrote the advanced linear algebra. The same person. Oh, this is, by the way, the hardest linear algebra book I've ever seen. This is the hardest book on linear algebra I've ever seen. By the way, this is, I mean, I don't know what to make of this book, but basically this is perhaps, I didn't even know there's so much linear algebra I don't know yet. But yeah, if you guys are fond of linear algebra, which I think everyone should be, there's no such thing as learning too much linear algebra in both pure and applied aspect. Yeah, go check out this book on advanced linear algebra. Okay. Yeah, I only wish he kept the optimization portion and fixing the mistakes. Okay. So yeah. All right. That's it for today. Thank you very much for joining the stream once again. This has me thinking about how many mistakes might exist in the archive might find now. There's gonna be tons of mistakes, and that's totally normal, dude. Grilling and chilling, that's totally normal. In fact, I'm working on a video on uniform continuity. Right? I think most of you must have heard of uniform continuity. Uniform continuity was something that Cauchy didn't understand, okay, or wasn't aware. So at Cauchy's time, there was still no notion of uniform continuity. But because he didn't distinguish it from regular continuity, a lot of his proofs were wrong. And that's totally normal. And that's totally no. It's just the nature of math. Like many proofs were supposedly proved, but later on discovered to have mistake, either by the author himself or herself or by others. This totally happened. Yeah, surprised that one person can write on math, finance, and all those pure math topics. Yeah, I know, right? This is perhaps a bit of an anomaly in Western academia, because in Western academia, things are more highly specialized, but not so much, right? You guys know Simmons. You guys know Simmons? Chern Simmons. Simmons is the guy who became Simmons Chern. The Simmons, not Chern, but Simmons. So Simmons started as, I think, pure mathematician. Yeah, he passed away not too long ago. Yeah, Simmons was mathematician, investor. So he did research on, I think, mathematical physics, differential geometry. Yeah, differential geometry, cryptography, and quantitative finance. I'm new here. What's your math background? Applied math and statistics. Yeah, so that's this is Simmons. So he did differential geometry, string theory. Yeah, so it's a very famous person. Renaissance Technologies. That's a hedge fund company. Yes, Stephen Roman is highly reputable. He certainly knows his stuff. I'm just like a little bit surprised about the number of mistakes here. Which uni? Which uni? Regular viewers probably already know because I often recommend stuff from a particular website. Yeah, I'm from Waterloo. I often recommend this linear algebra resource, and I quote it probably as often as I do from Axler. Yeah, Men Who Solved the Market, good book. Yeah, but it doesn't matter. Like I don't really care about the formal background anymore because I figured, there's so much math freely available that anybody who is determined can become a mathematician. Yeah, I said it right here. So it's really not that important. Okay, it's really not that important if you are motivated. So that's why I don't really usually talk about like formal credentials and stuff. I figured it's not as interesting as talking about actual math. So we'll just leave it there. All right. All right, guys. Thank you very much for watching the stream. Let me know if you guys enjoyed it in the comment. We might have to return to this subject perhaps in a future stream. I don't know what time. Okay, I can't promise anything because the next week's Saturday is on optimal control, and the Saturday after that is information. If one is not able to choose math and major, choose one of the engineering branches too. Yeah, you can certainly. Certainly, it is completely possible. It is completely possible. It is completely possible, and in fact, math is so huge. Not even math majors knows much of the math. Like, for example, I'm a complete beginner when it comes to algebra. I mean, I have a formal credential. If you ask me, say, things about abstract algebra, I would be pretty ignorant about them. I mean, which is okay. You don't need to know all the math. Like, just chill. Like, isn't it such a nice thing that there is no such thing as learning all the math? You can always have some fun. You can always have something to do. It's like inexhaustible resource. It's like oil that can't be used up. So isn't that nice? It doesn't matter what your formal background is. If you're interested in math, you can do it. because this is not magic. Right? It's never magic. It does not require a special brain to do math. Okay, um, some people might be a little bit faster or slower, but speed are irrelevant. Because individual standards differ. Some people prefer to sink a little bit deeper than usual. Some people are satisfied with solving a particular problem. Both are okay. How much taking math is major important for getting to financial quant? Well, fit for financial quant is you need a lot of math, right? Okay. So, and just in case you guys wonder what sort of math you need to do finance quant, to do quant finance, and here's a little suggestion. And not just suggestion, but not from me, but it's the University of Waterloo mathematical finance degree requirement. Okay, and you can check those out. There's a lot, right? So there's a lot. So that's mathematical finance degree. What courses you will take in mathematical finance? You go click here. This is the first year stuff. After first year, view all the courses required for your degree. Okay. For example, if you click here, you see introductory financial mathematics, investment science, corporate finance, and whatnot. You can ask me. I can probably find the name of the textbook if you want. You need to take measure theory in your first year. God bless. And there's some optional ones. You can take one of the following. Right? You can take one of the followings. Looks like you need computational stuff, differential equations. One of the following. These are perhaps the better one would be optimization because it's so relevant, and one of the high-level electives. So basically, that's kind of the gist of it. Okay, you need a lot of math. Is this all learning by self possible? Yeah, it is totally possible. You can learn everything. You can learn every math you want, bro. You can learn every math you want if you are determined. Okay, it's never about, like mathematics is the cheapest science possible. You just need, well, you need some books and you just need pen and pencil. That's it. At certain point, for quant, you would probably need a laptop, which is not a terribly high bar, and you can always do it yourself, provided you are motivated. Okay, provided you're motivated, and of course, we don't mean doing everything alone. Okay, self-study does not mean self-isolation. Right? You can always go to Discord, ask questions. For a start, you can reach out to like-minded people. So it's not always easy to do so, but I'm talking about like doing by yourself. I mean, you don't need to follow a lecture. The books are there. The exercises are there. The bulk of the work is done by self and self only. Even though if you go to lecture, like still 95% of the work is done by yourself. So choosing math major is not important as just learning, no matter how hard, when you can learn, right? In principle, yes. Okay, in principle, that is completely true. In principle, that is completely true. So, but while we live in this world, this real world, having a credential helps with the exterior, right? Having a credential helps with if, let's say, if you know all of this, okay? So if you know all of this material, but you don't have a degree, it is going to be, let's not fool ourselves, it's going to be difficult for you to get an actual job, say, than someone who have a degree. But do not mistake a degree with competence, okay? These two are, well, let me just put it this way. These are positively correlated. Having a prestigious degree is positively correlated to actual competence, but it's only a proxy. It's only a proxy. So if you're, let's say, if you're determined to learn this stuff and to make the connection between like self-mastery, right, and getting a job, there's going to be some risk involved, right? There's going to be some risk. There's some sort of luck element. You have to, at some point, know the right person to get into those positions. Like, okay, but as far as math is concerned, that is a overwhelmingly a solitary endeavor. Right? So as far as just learning the math and doing math is concerned, it is overwhelmingly speaking a solitary endeavor. And everything else, when it comes to, okay, if you're just talking about like mastering the mathematics, everything else is secondary. Everything is right. So, but how do you convert that human capital, quote unquote? How do you convert that human capital, quote unquote, to, let's say, a well-paying job or some other shenanigans? Then that's a different story. Right? But just learning the math itself is a overwhelmingly solitary endeavor. You do it yourself. Even when you have a good professor, you still do most of the work yourself, because the insight that the professor tells you in a lecture is not the same as the one you work out in exercise. It's a totally different experience. Okay? So, I mean, I really got to go. Thank you very much for watching. It's going to be a busy day for me because I'm having another live stream this evening because I can't do it on Saturday, on Sunday, this Sunday. Okay? I'll see you guys then. Bye now.